Welcome to Scientific Discovery Hub, where we dive into the mind-bending mysteries of the universe. Today we are exploring one of the most enigmatic puzzles in science, dark matter. Imagine a cosmic scaffolding invisible to our eyes, holding galaxies together like an unseen spiderweb. Sounds like science fiction? That's because dark matter, the mysterious substance making up 27% of the universe, defies everything we thought we knew about reality. What if I told you that galaxies wouldn't exist without it? Dark matter doesn't emit light, absorb energy, or interact with ordinary matter, except through gravity. First hinted at by Swiss astronomer Fritz Zwicky in the 1930s. This missing mass explains why galaxies spin wildly fast without flying apart. But how did we discover it? And why does it shape the universe's architecture? In this video, we'll unravel the invisible backbone of the cosmos, starting with Zwicky's groundbreaking calculations and Vera Rubin's galaxy rotation studies. We'll explore how dark matter acts as gravity's silent partner, weaving a cosmic web of filaments and voids that dictate where galaxies form. We'll follow the Milky Way's journey toward the Great Attractor, a gravitational behemoth hidden in plain sight, and venture into labs hunting for phantom particles like WIMPs and Axions. Along the way, we'll compare dark matter to its shadowy cousin, dark energy, and use supercomputer simulations to map the universe's hidden structure. But dark matter isn't just a scientific riddle, it's a philosophical conundrum. How do we study something we can't see? Could it hint at parallel quantum realms, or rewrite Einstein's theories? We'll even trace its fingerprints back to the Big Bang, revealing how quantum ripples from the dawn of time shape today's cosmos. Whether you're a curious stargazer or a seasoned sci-fi fan, this video will take you on a journey through the invisible forces that bind the universe. Hit play to uncover the secrets of dark matter, and don't forget to subscribe for more deep dives into the wonders of science. Let's turn the invisible visible together. In the vast, uncharted expanse of the cosmos, where galaxies spiral like painted whirlpools and stars burn with the fury of ancient furnaces, there exists a silent architect. This architect is neither seen nor heard, yet its influence binds the universe together in an intricate dance of balance and motion. It is the invisible scaffold, a ghostly lattice woven through the fabric of space, holding galaxies in place with an unseen hand. This enigmatic entity is known as dark matter, a substance that defies our senses, eludes direct detection, and yet accounts for nearly a quarter of the universe's composition. To grasp its significance is to confront the limits of human perception and the profound mysteries that lie beyond the veil of ordinary matter. What does it mean for something so abundant to be so utterly hidden? Dark matter does not emit light, nor does it absorb or reflect it, rendering it invisible to even the most advanced telescope. Yet its gravitational pull is undeniable, shaping the orbits of galaxies, the distribution of cosmic structures, and the ultimate fate of the universe itself. Imagine a colossal spiderweb stretched across the night sky, its threads invisible to the eye but perceptible only through the tremors they cause in the stars and gas that drift through them. This is the cosmic scaffolding upon which the universe is built, a structure so vast and complex that it challenges our understanding of reality. The more we probe the depths of the cosmos, the more we realize that what we perceive as the universe, the luminous stars, the swirling nebulas, the planets and moons, is merely a fraction of the whole. The rest lies in shadow, waiting to be understood. The mystery of dark matter is not just one of physics, but of philosophy. It forces us to reconsider what constitutes existence. If something cannot be seen, does it cease to be real? Or does its influence, its gravitational grip on the cosmos, grant it a kind of reality that transcends our sensory limitations? These questions echo through the corridors of science, reminding us that the universe is far richer and stranger than our current knowledge allows. As we peer deeper into the night sky, we are met not with answers, but with a growing awareness of how much remains beyond our reach. In this silent architecture of the cosmos, we find both the limits of our understanding and the boundless potential for discovery. The story of dark matter begins in the 1930s, when the Swiss-American astronomer Fritz Zwicky peered into the Coma Cluster, a sprawling congregation of galaxies some 320 million light-years away. As he meticulously measured the velocities of these galaxies, a startling discrepancy emerged. The galaxies were moving far too quickly for the visible mass within the cluster to account for their motion. According to Newtonian physics, the gravitational pull exerted by the observable matter, stars, gas and dust, should have been insufficient to keep the galaxies from flying apart like shrapnel, yet they remained, locked in a cosmic embrace that defied explanation. Zwicky coined the term missing mass to describe the unseen force holding the cluster together, a term that would later evolve into the concept of dark matter. His calculations suggested that the true mass of the Coma cluster was hundreds of times greater than what could be observed, hinting at a vast reservoir of invisible material lurking in the voids between galaxies. Zwicky's insights were largely ignored for decades, dismissed as anomalies or miscalculations in an era when the idea of unseen mass seemed almost heretical. However, in the 1970s, American astronomer Vera Rubin would reignite the debate with her groundbreaking work on galaxy rotation curves. By studying the Andromeda Galaxy and others, Rubin observed that stars at the outer edges of galaxies moved at speeds that should have caused them to escape their gravitational bonds. Instead, they orbited as if tethered by an invisible force, their velocities remaining constant despite the decreasing density of visible matter. This observation shattered the prevailing assumption that the gravitational influence of a galaxy diminished with distance from its center. The only plausible explanation was that an immense amount of unseen mass, dark matter, was distributed throughout the galactic halo, providing the additional gravitational pull needed to hold the galaxy together. Further evidence emerged from the study of gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from distant galaxies passes through massive objects, such as galaxy clusters, the gravitational field bends the light, distorting the image of the background object. By analyzing these distortions, astronomers could map the distribution of mass in the universe, revealing that the majority of it was invisible. One of the most striking examples came from the Bullet Cluster collision, a cosmic event where two galaxy clusters collided at high speed. Observations showed that the bulk of the mass in the system, detected through gravitational lensing, was separated from the visible matter, which had been stripped away by the collision. This provided compelling evidence that dark matter existed independently of ordinary matter, interacting primarily through gravity and not through electromagnetic forces. These discoveries painted a picture of the universe as a web of dark matter, a vast cosmic scaffold upon which galaxies are strung like beads. Simulations of the early universe further reinforced this notion, showing that without dark matter, the formation of galaxies would have been impossible. The gravitational pull of dark matter acted as a seedbed for ordinary matter to coalesce, allowing stars and galaxies to take shape over billions of years. In this way, dark matter is not merely an invisible component of the cosmos, but a foundational element of its structure, a silent partner in the grand design of creation. Yet the question remains, what exactly is dark matter? Unlike ordinary matter, which is composed of protons, neutrons, and electrons, dark matter does not interact with light or any of the fundamental forces except gravity. It does not form atoms, nor does it emit or absorb radiation. Its existence is inferred solely through its gravitational effects, making it one of the greatest puzzles in modern physics. Some theories propose that dark matter consists of weakly interacting massive particles, WIMPs, hypothetical entities that rarely collide with ordinary matter. Others suggest it may be composed of primordial black holes or exotic particles yet to be discovered. Despite decades of research, no definitive detection has been made, leaving the nature of dark matter shrouded in mystery. The search for dark matter continues, driven by the tantalizing possibility that it may hold the key to unlocking the next chapter of our understanding of the universe. Experiments such as the Large Hadron Collider and underground detectors like the Lux Zeppelin experiment seek to capture the faintest whispers of dark matter particles colliding with ordinary matter. Meanwhile, astrophysicists analyze the cosmic microwave background, the afterglow of the Big Bang, for clues about dark matter's role in the early universe. Each new observation brings us closer to unraveling the secrets of this invisible scaffold, even as it reminds us of how much remains unknown. The implications of dark matter extend far beyond the mechanics of galaxy formation, challenging the very foundations of our understanding of physics and reality. At its core, dark matter represents a chasm in the standard model of particle physics, the framework that describes the fundamental particles and forces governing the universe. While the standard model accounts for ordinary matter and the interactions of subatomic particles, it offers no explanation for dark matter. This gap suggests either the existence of new particles that lie beyond the standard model, or the necessity of an entirely revised theoretical paradigm. The pursuit of dark matter is thus not merely an exploration of the cosmos, but a quest to redefine the laws that govern it. One of the most profound questions raised by dark matter is whether it interacts through forces other than gravity. If it does, those interactions must be extraordinarily weak, which would explain its invisibility. Theorists have proposed a range of possibilities, from Axions hypothetical particles that may arise from quantum chromodynamics to sterile neutrinos, which are heavier cousins of the elusive neutrinos detected in particle accelerators. Each candidate carries unique implications, not only for cosmology, but for the nature of reality itself. For instance, if dark matter particles annihilate or decay, they could produce detectable signals in the form of gamma rays or cosmic rays. Such a discovery would not only confirm the existence of dark matter, but also provide insight into its properties, potentially bridging the gap between particle physics and cosmology beyond the realm of particles. Dark matter's gravitational influence raises philosophical questions about the nature of existence. If the universe is predominantly composed of something we cannot see or touch, what does that say about our perception of reality? Our senses and instruments have evolved to detect the familiar light, sound, and matter in its visible forms, but they are blind to the vast majority of the cosmos. This realization humbles us, reminding us that our understanding is but a fragment of a much larger truth. It also invites speculation about whether dark matter might harbor its own forms of complexity or structure, though such ideas remain purely speculative. After all, dark matter's lack of interaction with electromagnetic forces means it cannot form atoms, molecules, or the structures necessary for life as we know it. Yet the mere possibility that it could give rise to phenomena beyond our comprehension opens the door to endless curiosity. Perhaps the most unsettling implication of dark matter is its challenge to the Copernican principle, the idea that Earth does not occupy a privileged position in the universe. If the universe is held together by an invisible scaffold, it suggests that our visible world is but a small part of a much vaster, unseen reality. This perspective shifts our place in the cosmos from a central role to a peripheral one, urging us to consider that the laws of physics we observe may be local manifestations of a deeper, universal order. In this context, dark matter becomes more than a scientific puzzle. It is a mirror reflecting the limits of human knowledge and the infinite scope of the unknown. The search for dark matter also underscores the interconnectedness of all things in the universe. Just as the gravitational pull of dark matter shapes the orbits of galaxies, so too do the actions of humanity ripple through the fabric of space-time. In our quest to understand the cosmos, we are not passive observers but active participants in the unfolding story of the universe. Every experiment conducted, every observation made, adds another thread to the tapestry of knowledge, weaving together the seen and the unseen. In this way, the pursuit of dark matter is a testament to the human spirit, a relentless drive to seek meaning in the void, to illuminate the shadows, and to glimpse the scaffolding that holds our universe together. To truly grasp the significance of dark matter, we must return to the moment when its presence first became evident, a time when the universe's hidden architecture began to emerge from the shadows. The 1930s, a decade marked by global upheaval and scientific revolution, saw Fritz Zwicky's pioneering work lay the groundwork for a paradigm shift in astronomy. His observations of the Coma cluster were not merely a mathematical curiosity, but a revelation that the universe was far more complex than previously imagined. Yet, as history often reveals, groundbreaking ideas are not always immediately embraced. Zwicky's findings were met with skepticism, his calculations dismissed by many as errors or anomalies in an era when the concept of unseen mass seemed implausible. The universe, after all, had long been understood as a realm governed by visible matter, and the forces that acted upon it. The idea that the cosmos harbored an invisible, omnipresent substance defied intuition and demanded a re-evaluation of the very principles that underpin celestial mechanics. This resistance to change is not uncommon in the annals of science. From the heliocentric model of the solar system to the theory of relativity, revolutionary ideas often face initial rejection before gaining acceptance. In Zwicky's case, the delay in recognition was partly due to the lack of technological advancements needed to verify his hypothesis. The tools required to measure the subtle gravitational effects of dark matter, high-resolution spectrographs, sensitive detectors, and sophisticated computational models were still in their infancy. It was not until the 1970s, with Vera Rubin's meticulous studies of galaxy rotation curves, that the evidence for dark matter became undeniable. Her work demonstrated that the visible matter in galaxies was insufficient to account for their rotational velocities, a finding that could only be explained by the presence of an unseen mass. This breakthrough reignited interest in Zwicky's earlier work, cementing dark matter as a cornerstone of modern cosmology. As we trace the path from Zwicky's initial observations to the present-day search for dark matter, we are reminded of the iterative nature of scientific discovery. Each step forward builds upon the work of those who came before, refining our understanding and expanding the boundaries of knowledge. The journey to unravel the mysteries of dark matter is not merely a technical endeavor, but a testament to human perseverance and ingenuity. It is a story of curiosity, of bold hypotheses tested against the vastness of the cosmos, and of the quiet persistence of those who dare to look beyond the visible and into the unknown. In the next segment, we will delve deeper into this history, exploring how the seeds of doubt and wonder sown in the 1930s have blossomed into one of the most profound quests in the history of science. In the vast, ever-expanding tapestry of the universe, where stars flicker like distant embers and galaxies spiral in silent harmony, humanity has long sought to decipher the laws that govern its grand design. From the earliest stargazers who charted the heavens to the modern astronomers peering through colossal telescopes, the cosmos has remained an enigmatic puzzle, its secrets hidden in the fabric of space-time. Yet, for all our progress in mapping the celestial sphere, the universe has always held mysteries beyond our grasp, questions that defy conventional wisdom and challenge the very foundations of physics. One such revelation emerged in 1933, when the Swiss astronomer Fritz Zwicky, working at the California Institute of Technology, stumbled upon a cosmic anomaly that would shake the field of cosmology to its core. Zwicky's discovery was born from meticulous observation and rigorous calculation. While studying the Coma Cluster, a vast congregation of galaxies, he noticed something perplexing. The individual galaxies within the cluster were moving at velocities far greater than could be explained by the gravitational pull of their visible mass. According to Newtonian physics, the speed at which galaxies orbit one another should depend solely on the amount of mass present. Yet the observed motion suggested that there was significantly more mass at play than what could be accounted for by the luminous stars and interstellar gas. The implication was staggering. Either Newtonian gravity was incomplete, or there existed an unseen form of matter exerting an invisible gravitational force. At the time, Zwicky's findings were met with skepticism. The idea that most of the universe's mass was hidden from view seemed almost absurd. After all, the cosmos had always been measured in terms of what could be seen: stars, nebulae, and the faint glow of distant quasars. To suggest that the majority of the universe's material was intangible, imperceptible, and yet fundamental to its structure was a radical proposition. Nonetheless, Zwicky persisted. He coined the term dunkel materie, or dark matter, to describe this elusive substance. His insight marked the beginning of a profound shift in our understanding of the universe, one that would take decades to fully appreciate. Though Zwicky's discovery was initially overlooked, it planted the seed for one of the greatest scientific quests of the 20th and 21st centuries. The search for dark matter became a driving force in astrophysics, compelling researchers to refine observational techniques, develop new theoretical frameworks, and explore the very limits of human knowledge. What began as a single astronomer's perplexing calculation would eventually reshape our perception of reality itself, revealing a cosmos far more intricate and mysterious than we had ever imagined. Fritz Zwicky's groundbreaking insight did not arise from mere speculation. It was the result of precise and methodical observations. Using spectroscopic measurements, he analyzed the Doppler shifts of light emitted by individual galaxies within the Coma cluster. By measuring how much the spectral lines of these galaxies were red-shifted or blue-shifted, Zwicky could determine their velocities relative to Earth. According to Newtonian gravity, the gravitational pull of visible matter, stars, gas clouds, and other luminous components should dictate how fast these galaxies moved within the cluster. However, when Zwicky calculated the expected orbital speeds based on the visible mass, he found a startling discrepancy. The galaxies were moving far faster than they should have been. To understand the full magnitude of this anomaly, consider a simple analogy. Imagine a group of cars traveling around a circular track. If the track is frictionless and the only force acting upon them is gravity, the car's speed should be determined by the mass of the track and the distance from its center. If the cars are moving faster than expected, one might assume that either the mass of the track is greater than measured, or that some external force is influencing their motion. In Zwicky's case, the galaxies were the cars, and the gravitational force acting upon them was far stronger than predicted by the visible mass alone. This led to an inescapable conclusion. There had to be an unseen form of mass, providing the additional gravitational pull necessary to keep the galaxies from flying apart. Zwicky estimated that the total mass of the Coma cluster was approximately 10 times greater than the mass inferred from its luminous components. This implied that an enormous amount of matter, something invisible and undetectable by traditional means, was exerting a gravitational influence. At the time, such a notion was unprecedented. The prevailing assumption was that the universe's mass was composed almost entirely of the luminous matter we could see: stars, planets, nebulae, and interstellar gas. The idea that the majority of a galaxy cluster's mass was hidden from view challenged not only the understanding of gravity, but also the very foundation of astrophysical theory. Despite the significance of his findings, Zwicky's conclusions were largely ignored for decades. Many astronomers found the concept of invisible mass implausible, and without further corroborating evidence, his hypothesis remained on the fringes of mainstream science. However, the seeds of doubt he sowed would eventually bear fruit. In the 1970s, American astronomer Vera Rubin would build upon Zwicky's work by examining the rotational speeds of individual galaxies. Her observations of the Andromeda Galaxy and others revealed a similar pattern. The outer regions of galaxies rotated at speeds inconsistent with the visible mass alone. This independent confirmation of Zwicky's original hypothesis would reignite interest in the enigma of dark matter, setting the stage for one of the most profound scientific inquiries of the modern era. By the time Zwicky's work was fully appreciated, the scientific community had come to accept that the universe was not as it appeared. The visible stars and galaxies constituted only a small fraction of the cosmos' true mass. The rest, hidden from sight, was a cosmic enigma waiting to be unraveled. This realization marked the beginning of a new chapter in astrophysics, one defined by the search for a substance that defied detection yet shaped the very architecture of the universe. Zwicky's discovery did more than challenge the laws of physics. It forced humanity to confront the limitations of its own perception. For millennia, we have relied on sight as our primary means of understanding the universe. The stars above, the glimmer of distant galaxies, and the faint glow of interstellar dust have served as our guideposts in the vast cosmic expanse. Yet, Zwicky's work revealed that the visible universe was but a fragment of a far grander, unseen reality. If the majority of a galaxy's mass could not be seen, if the very fabric of space-time was influenced by an invisible force, then what else lay beyond our grasp? The realization that we could be blind to the fundamental architecture of the cosmos was both humbling and unsettling. This epiphany sent ripples through the scientific community, shaking the foundations of physics and cosmology. Newtonian gravity, which had governed our understanding of motion for centuries, suddenly appeared insufficient. Einstein's general relativity, which described gravity as the curvature of space-time, offered a more comprehensive framework, yet even it struggled to account for the sheer scale of the discrepancies Zwicky uncovered. The equations worked, but the underlying assumptions did not. If gravity operated as expected, then the observed motions of galaxies demanded a mass that simply wasn't there. This paradox left physicists with two possibilities. Either gravity behaved differently on cosmic scales, or something fundamentally unknown was at play. The latter possibility, that an unseen form of matter exerted a gravitational influence, became the dominant hypothesis. Dark matter, as it came to be known, was not merely a curiosity. It was a necessity for explaining the dynamics of the universe. Without it, galaxies would not hold together. Without it, the vast cosmic web of structure we observe today would not exist. The implications were staggering. The universe was not composed primarily of the luminous matter we could see, nor of the familiar elements that formed stars and planets. Instead, the bulk of its substance remained hidden, a ghostly presence that shaped the cosmos from the shadows. This revelation forced a radical shift in how scientists approached the universe. No longer could they rely solely on what was visible. They had to seek out the invisible. New instruments were developed, new experiments devised, all aimed at detecting the unseen. Particle accelerators sought to recreate the conditions of the early universe in hopes of producing dark matter particles. Radio telescopes scanned the sky for indirect signals of its presence. Space-based observatories mapped the distribution of mass across the cosmos, using gravitational lensing to infer the locations of dark matter's hidden influence. The search for dark matter became one of the most ambitious scientific endeavors of the modern era, driven by the need to reconcile observation with theory. Yet, despite decades of effort, dark matter remained elusive. No direct detection had been made. Its properties, what it was composed of, how it interacted with ordinary matter, remained shrouded in uncertainty. Some proposed that it consisted of weakly interacting massive particles, WIMPs, hypothetical entities that barely interacted with anything except through gravity. Others suggested it might be composed of primordial black holes, or Axions, exotic particles that had yet to be discovered. Each hypothesis opened new avenues of inquiry, but none provided definitive answers. The more scientists learned, the more they realized how little they truly understood. Beyond the realm of particle physics, Zwicky's discovery also reshaped our understanding of the universe's evolution. The distribution of dark matter played a crucial role in the formation of galaxies and large-scale structures. Simulations showed that without its gravitational scaffolding, the universe would look vastly different. Stars would not have coalesced into galaxies, and the vast cosmic filaments we observe today would not exist. The presence of dark matter was not just a cosmic oddity, it was the unseen architect of the universe itself. As the search for dark matter continued, it became clear that this mystery was not merely an academic exercise. It was a fundamental question about the nature of reality. If the majority of the universe was invisible, then what did that say about our ability to perceive it? Were we limited by the tools at our disposal, or was there an inherent constraint to human understanding? These questions extended beyond physics into philosophy, challenging our assumptions about the nature of knowledge and the boundaries of perception. The universe, once thought to be comprehensible through observation and reason, had proven itself to be far more enigmatic than we had ever imagined. Dark matter may be unseen, yet its gravitational influence shapes the universe in ways both subtle and profound. It is the silent hand guiding the dance of galaxies, the unseen scaffold upon which the cosmic web is built. Without its gravitational pull, the vast structures we observe, galaxy clusters, superclusters, and the great cosmic filaments stretching across billions of light years, would not exist in their current form. It is as though the universe is held together by an invisible lattice, a ghostly glue binding the luminous stars and gas into the grand architecture of space. Consider the galaxies themselves. Their outer regions rotate at speeds that defy explanation, based solely on the mass of visible stars and gas. The only way to reconcile this discrepancy is to posit the existence of a vast halo of dark matter surrounding each galaxy, extending far beyond the reach of its luminous components. These halos act as gravitational anchors, preventing galaxies from tearing apart under their own motion. Without them, the Milky Way and its stellar neighbors would likely disintegrate, their stars scattering into the void. Instead, they remain intact, their delicate balance maintained by the unseen force of dark matter. On a larger scale, the distribution of dark matter dictates the formation of cosmic structures. Simulations of the early universe show that without dark matter's gravitational pull, ordinary matter would not have clumped together quickly enough to form the first stars and galaxies. Instead, dark matter acted as a cosmic scaffold, providing the gravitational wells into which ordinary matter could collapse. Over billions of years, this interplay between dark and visible matter gave rise to the intricate web of galaxies we see today. The universe is not a random collection of stars, but a carefully woven tapestry, with dark matter serving as its foundational thread. Even more intriguing is the fact that dark matter does not interact with light. Unlike ordinary matter, which emits, absorbs, or reflects electromagnetic radiation, dark matter neither shines nor obscures. It passes through ordinary matter without resistance, making it nearly impossible to detect directly. Yet, its influence is undeniable. Gravitational lensing, the bending of light by massive objects, provides indirect evidence of its presence. When light from distant galaxies travels through the cosmos, it bends around massive structures that appear far more massive than their visible components would suggest. This distortion reveals the hidden gravitational pull of dark matter, allowing astronomers to map its distribution across the universe. Though dark matter remains one of the greatest mysteries of modern science, its role in shaping the cosmos is undeniable. It is the unseen force that holds galaxies together, the invisible architect that guided the birth of stars and the formation of the cosmic web. As we continue to probe its nature, we are not merely searching for an elusive particle, we are seeking to understand the very blueprint of the universe itself. The universe is a symphony of motion, a grand ballet choreographed by forces unseen. At its heart lies gravity, the ancient alchemist that transforms the raw chaos of the cosmos into the ordered elegance of stars, galaxies, and the vast celestial dance of cosmic bodies. Yet this dance is not performed alone. A shadowy partner, silent and elusive, has guided every step since the dawn of time. This is dark matter, the invisible scaffold upon which the universe is built, the unseen force that binds galaxies into clusters, and the mysterious substance that ensures the cosmos remains structured rather than dissolving into entropy. Imagine a universe without dark matter, a realm where gravity, though potent, lacks the leverage to shape the vastness of space. Stars would never coalesce. Galaxies would scatter like dust in a storm. The familiar spirals of the Milky Way, the elliptical halos of Andromeda, the Great Virgo cluster, all would vanish, replaced by a featureless void. Dark matter is not merely an afterthought in the story of the cosmos. It is the foundation, the unseen hand that sculpts the universe into a habitable, comprehensible whole. Yet, for all its influence, dark matter remains a riddle. Unlike ordinary matter, it does not emit light, nor does it interact with the electromagnetic force that governs the behavior of atoms and molecules. It is a ghostly presence, detectable only through its gravitational fingerprints, the subtle distortions it imprints on the orbits of stars, the bending of light from distant quasars, and the clumping of galaxies into vast cosmic webs. To speak of dark matter is to speak of the unknown, of a substance that defies our most advanced instruments, yet reveals itself through the very laws of physics we thought we understood. This duality, its simultaneous invisibility and indispensable role, invites a profound reflection. How can something so fundamental to the universe remain hidden from direct observation? What truths lie buried in the silent architecture of dark matter, waiting to reshape our understanding of existence? As we peer deeper into the cosmos, we find ourselves not just observers of the universe, but participants in a dialogue with forces older than time itself. The story of dark matter begins in the earliest moments of the universe, mere fractions of a second after the Big Bang. In that primordial fireball, the fabric of space was a seething cauldron of energy and radiation. Ordinary matter, protons, neutrons, electrons, was born in this crucible, but it was too hot and dense for stable atoms to form. Yet even in this chaos, dark matter already existed, a relic of an era when the laws of physics operated under rules now forgotten. What was dark matter at this stage? The answer lies in the quantum fluctuations of the early universe. These tiny ripples in the density of dark matter acted as seeds for the cosmic structures we see today. Imagine a vast ocean, its surface disturbed by the faintest breeze. Where waves rise slightly higher, they create regions of greater density. In the case of the universe, these density peaks became gravitational wells, drawing in surrounding material like moths to a flame. But here, the moths were photons and neutrinos, and the flame was the unseen gravity of dark matter. As the universe expanded and cooled, dark matter's influence grew. Because it does not interact with light, it could clump together freely, forming vast halos that stretched across millions of light years. These halos were not solid structures, but diffuse clouds of mass, their gravitational pull acting as a kind of scaffolding for ordinary matter. When the first atoms finally formed, hydrogen and helium, their gas clouds began to drift toward the centers of these dark matter halos. Over eons, the gas collapsed under its own gravity, igniting into the first stars and galaxies. This process is akin to a sculptor working with a preformed mold. The dark matter halos provided the framework, the blueprint, within which ordinary matter could organize itself. Without this scaffold, the gas would have remained dispersed, unable to overcome the repulsive forces of radiation pressure and thermal motion. The result would have been a universe devoid of structure, where stars and galaxies never formed, and the conditions for life would have been impossible. Observational evidence supports this cosmic collaboration. The rotational speeds of galaxies, for instance, reveal a discrepancy. The visible matter alone cannot account for the gravitational forces holding them together. The same is true for galaxy clusters, where the mass inferred from gravitational lensing far exceeds the sum of their luminous components. These anomalies are the fingerprints of dark matter, etched into the universe's history. Moreover, the cosmic microwave background, CMB, the afterglow of the Big Bang, offers a snapshot of the universe when it was just 380,000 years old. Tiny temperature fluctuations in the CMB correspond to density variations in the early universe. These fluctuations align perfectly with the predictions of models that include dark matter, confirming its role as the silent architect of cosmic structure. Thus, dark matter is not a mere curiosity. It is a cornerstone of cosmology. It explains the distribution of galaxies, the formation of superclusters, and the large-scale geometry of the universe. Its gravity shaped the cosmos, ensuring that the universe evolved into the intricate, star-filled expanse we inhabit today. Despite its central role in the universe, dark matter remains a paradox, a substance that exerts gravitational influence, yet refuses to reveal itself in any other way. This duality raises profound questions about the nature of reality. What is dark matter made of? Why does it interact only through gravity and the weak nuclear force? And if it is so abundant, why does it remain undetected in our laboratories? These mysteries challenge the boundaries of modern physics and invite speculation that transcends the known laws of nature. One leading hypothesis posits that dark matter consists of weakly interacting massive particles, WIMPs, hypothetical particles that interact through gravity and the weak force but not electromagnetism. If WIMPs exist, they would rarely collide with ordinary matter, making them incredibly difficult to detect. Another candidate is the Axion, a lightweight particle proposed to resolve discrepancies in quantum chromodynamics. Both theories suggest that dark matter is a remnant of the Big Bang, a leftover particle that failed to annihilate itself in the universe's infancy due to its minimal interactions. Yet some scientists argue that dark matter may not be composed of particles at all. Alternative theories, such as modified Newtonian dynamics (MOND), propose that our understanding of gravity is incomplete. In this view, the observed gravitational effects attributed to dark matter arise not from unseen mass, but from a tweak to Einstein's equations, particularly in regions of low acceleration. While MOND successfully explains certain galactic phenomena, it struggles to account for the full breadth of observational data, including the behavior of galaxy clusters and the CMB. The implications of dark matter extend beyond particle physics. Its existence suggests that the universe is far stranger than we imagine. If dark matter is indeed a new form of matter, it would require a revision of the standard model of particle physics, which currently accounts for only 4% of the universe's mass-energy content, the remaining 96% comprising dark matter, and dark energy is an abyss of unknowns, a frontier that may hold the key to a unified theory of everything. Philosophically, dark matter compels us to confront the limits of human perception. We are creatures bound to the electromagnetic spectrum, attuned to the world of light and matter, yet the majority of the universe operates in realms beyond our senses, governed by forces we barely comprehend. This realization humbles us, reminding us that the cosmos is not a puzzle we are meant to solve, but a mystery to be revered. Furthermore, dark matter's passivity, its refusal to emit, absorb or reflect light, highlights the fragility of our knowledge. Science thrives on observation and experimentation, yet dark matter eludes both. Its detection relies on indirect methods, such as mapping the gravitational distortions it causes in visible matter. This reliance on inference underscores the provisional nature of scientific truth and the importance of humility in the face of the unknown. As we probe deeper into the enigma of dark matter, we are also reminded of the interconnectedness of the universe. The same dark matter that shaped the first galaxies now permeates our solar system, passing through Earth and our bodies at a rate of billions per second. Though imperceptible, it is a constant companion, a reminder that we are embedded in a cosmos far vaster and more intricate than our senses can perceive. If dark matter is the unseen scaffold of the universe, it is also the thread that weaves the cosmos into a grand tapestry. The structures we observe, galaxies, clusters and superclusters, are not scattered randomly, but arranged in a vast interwoven network known as the cosmic web. This web, stretching across billions of light years, is the ultimate expression of dark matter's gravitational influence. Filaments of galaxies trace the edges of dark matter halos, while immense voids yawn between them, creating a pattern reminiscent of a spider's silk or the neural connections of a brain. To understand this architecture is to glimpse the universe's blueprint. The cosmic web is not a static relic, but a living entity, evolving as dark matter continues to shape the distribution of matter over time. Within its threads lie the stories of galactic collisions, the birth of stars, and the slow, inexorable march of time. Yet, much remains hidden. What lies at the heart of these filaments? How do dark matter and dark energy, the mysterious force driving the universe's accelerated expansion, interact to determine the web's future? In the next segment, we will journey into the depths of this cosmic web, unraveling the threads that connect galaxies and revealing the unseen forces that bind the universe together. We will explore how dark matter's invisible hand continues to guide the fate of stars and civilizations alike, shaping a cosmos that is both infinitely complex and profoundly interconnected. Above us, the cosmos sprawls in a dazzling tapestry of stars, nebulae, and distant galaxies, a glittering expanse that has captivated humanity for millennia. Yet, if we could strip away the visible universe, the luminous stars, the swirling clouds of gas, the radiant halos of quasars, we would uncover a far stranger and more profound reality. Beneath the shimmering veil lies a vast invisible scaffold, a ghostly architecture woven from a substance we cannot see, touch, or fully comprehend: dark matter. This enigmatic material forms a sprawling cosmic web, a labyrinth of filaments and voids stretching billions of light years across the universe. It is the silent architect of the cosmos, the unseen hand that guides the birth and motion of galaxies, shaping the very structure of our observable reality. The cosmic web is not a mere abstraction, but a cornerstone of modern cosmology. Its existence was first hinted at in the 1930s by the Swiss astronomer Fritz Zwicky, who noticed that the mass of visible matter in galaxy clusters was insufficient to account for their gravitational behavior. Decades later, as telescopes peered deeper into space and simulations modeled the universe's evolution, the cosmic web emerged as a central pillar of the lambda-cold dark matter, the LAMCDM model. This framework describes a universe dominated by dark matter, an elusive substance that interacts primarily through gravity and does not emit, absorb, or reflect light. Without dark matter's gravitational pull, the universe as we know it would unravel. Galaxies would not form, stars would not ignite, and the intricate dance of celestial bodies would collapse into chaos. To grasp the scale of the cosmic web is to confront the staggering immensity of the cosmos. Imagine a spiderweb so vast that its threads stretch across the observable universe, spanning over 90 billion light-years. At its nodes lie clusters of galaxies, each containing hundreds or thousands of individual star systems. Between them, colossal voids yawn empty, vast enough to swallow entire superclusters whole. This structure, though invisible to the naked eye, is etched into the fabric of space-time itself, a testament to the universe's hidden order. Understanding the cosmic web is not merely an exercise in curiosity. It is a quest to decode the fundamental principles that govern existence. The cosmic web arises from the interplay of gravity and the universe's expansion, a delicate balance that has shaped the cosmos for nearly 13.8 billion years. In the earliest moments of the universe, quantum fluctuations imprinted faint ripples onto the primordial plasma, which, as the cosmos cooled and expanded, evolved into regions of slightly denser matter. These density variations acted as seeds for gravitational collapse. However, ordinary matter, the stuff of stars and planets, was insufficient to drive the formation of large-scale structures. Enter dark matter, a mysterious substance that constitutes approximately 27% of the universe's mass-energy content. Unlike normal matter, dark matter does not interact via electromagnetic force, meaning it neither emits nor absorbs light. Instead, it responds solely to gravity, allowing it to clump together freely in the early universe. As gravity drew dark matter into dense knots, it formed a vast network of filaments. These threads, often spanning millions of light-years, acted as gravitational highways, guiding the flow of ordinary matter into their embrace. Over billions of years, gas clouds composed of hydrogen and helium were funneled along these dark matter filaments, coalescing into proto-galaxies at the intersections of the web. Today, these junctions host galaxy clusters, while the filaments themselves contain long thread-like distributions of galaxies. The voids between these structures, in stark contrast, are nearly devoid of both dark and ordinary matter, creating a latticework of immense scale. This hierarchical structure is best visualized through cosmological simulations, such as the Millennium Simulation or the Illustris NG project. These computational marvels track the evolution of dark matter and baryonic matter from the universe's infancy to the present day. In these models, dark matter particles behave like a pressureless fluid, collapsing under self-gravity to form halos. Within these halos, ordinary matter accumulates, eventually igniting into stars and galaxies. The simulations reveal a universe teeming with complexity. Networks of filaments crisscross the cosmos, with galaxy clusters forming at their densest points. The results align remarkably well with observational data, lending credence to the LAMCDM model. Observational evidence further confirms the cosmic web's reality. Surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DS, have mapped the distribution of galaxies across the sky, revealing a pattern that mirrors the predictions of dark matter simulations. Additionally, the cosmic microwave background, CMB, a relic of the early universe, contains subtle temperature fluctuations that correspond to the density variations imprinted by dark matter. These anisotropies, measured by satellites such as Planck, provide a snapshot of the cosmic web in its infancy, showing how the seeds of structure were sown. Gravitational lensing studies also offer indirect glimpses of the web's architecture. By analyzing how light from distant galaxies bends around massive objects, astronomers can reconstruct the distribution of dark matter, unveiling its filamentary nature. The cosmic web is not static but dynamic, evolving as the universe expands. Dark energy, the mysterious force driving the accelerated expansion of space, ensures that the voids will grow larger over time, while the filaments remain tethered by gravity. This interplay between dark matter and dark energy shapes the fate of the cosmos, determining whether the web will persist or unravel in the distant future. Yet despite these insights, the nature of dark matter itself remains one of the greatest unsolved mysteries in physics. Is it composed of weakly interacting massive particles, WIMPs axions, or something entirely different? The answer may lie buried within the cosmic web structure, waiting to be uncovered by future observations. The cosmic web is more than a structural blueprint for the universe. It is a profound testament to the interplay of forces that govern existence. Its existence implies a universe finely balanced between chaos and order, where the invisible hand of dark matter orchestrates the grand symphony of galaxies. This balance raises deep questions. Why does the cosmic web take the form it does? What does its structure reveal about the laws of physics, the origins of the universe, or even the nature of reality itself? To explore these questions is to peer into the heart of cosmology, where theory and observation converge to illuminate the cosmos's hidden logic. One of the most striking implications of the cosmic web is its role in the formation of life. The web's architecture ensures that galaxies are distributed in a way that allows for the stable orbits of stars and planetary systems. If dark matter had been less abundant or distributed differently, galaxies might have collapsed into monolithic black holes or dispersed into isolated stars, precluding the conditions necessary for complex chemistry and life. This apparent fine-tuning has led some physicists to ponder whether the universe's structure is a product of chance, necessity, or something beyond our current understanding. While the LNCDM model explains the web's formation through known physics, the precise values of constants like the density of dark matter and dark energy remain unexplained, hinting at deeper principles yet to be discovered. The cosmic web also challenges our understanding of gravity. Einstein's general theory of relativity predicts that massive objects warp space-time, guiding the motion of matter through gravitational attraction. However, the distribution of dark matter in the web suggests that gravity operates on scales, where quantum effects may become relevant. Could the interplay between general relativity and quantum mechanics, currently incompatible, be reconciled through a study of the web's structure? Some theorists propose that dark matter might exhibit quantum coherence over astronomical distances, a phenomenon that could bridge the gap between the macroscopic and microscopic worlds. Others speculate that the web's stability hints at modifications to gravity itself, such as those proposed by theories like modified Newtonian dynamics, MOND. While the cosmic web largely supports general relativity, its intricate patterns invite scrutiny of the assumptions underlying our gravitational models. Beyond physics, the cosmic web invites philosophical reflection. To stand beneath the stars and realize that their arrangement is dictated by an invisible scaffold is to confront the humbling vastness of the unknown. The web's existence reminds us that the universe is a tapestry of interconnectedness, where every galaxy, star, and planet owes its position to forces we cannot directly perceive. This realization fosters a sense of unity and perspective. Earth is but a speck within a node of the web, and yet the same physical laws that shape the cosmos apply equally to the atoms in our bodies. The cosmic web thus serves as a metaphor for the hidden connections that bind all things, from the subatomic to the cosmic. Despite the progress made in understanding the web, many mysteries endure. What is the true identity of dark matter? Does it consist of particles, fields, or something else entirely? How did the initial density fluctuations that seeded the web arise? Could the web's structure provide clues about the universe's inflationary epoch, the period of rapid expansion just after the Big Bang? These questions fuel ongoing research, from underground detectors searching for dark matter particles to space-based observatories mapping the distribution of galaxies. Each new discovery brings us closer to unraveling the cosmic web's secrets. Yet the journey is far from complete. Perhaps the most profound implication of the cosmic web is its capacity to inspire wonder. In tracing its invisible threads, we glimpse the elegance of a universe governed by elegant equations and profound symmetry. The web is a reminder that the cosmos is not a random collection of objects, but a coherent whole, shaped by forces that transcend human perception. As we continue to probe its depths, we are not merely cataloging data. We are participating in a timeless dialogue between humanity and the universe, seeking to understand our place within its infinite expanse. Yet, for all its grandeur, the cosmic web is not without contradictions. While dark matter's gravitational influence has sculpted galaxies into its intricate lattice, certain celestial bodies defy this cosmic blueprint. Some galaxies rotate in ways that challenge Newton's laws of motion, their outer stars moving faster than expected without sufficient visible mass to account for their speed. Others exist in isolation, seemingly untethered to the web's filaments, their formation unexplainable by standard models. These anomalies whisper of a universe more complex than our current understanding allows, hinting at the need to revise the very foundations of physics. What if the cosmic web is not the final answer, but merely one piece of a larger puzzle? What if the laws of gravity themselves require modification to account for the universe's most perplexing phenomena? In the next segment, we turn our gaze to the galaxies that rebel against the cosmic order, exploring the frontiers of modified gravity theories and the tantalizing possibility that Newton's laws may not hold dominion over the entire cosmos. As we venture further into the unknown, we are reminded that the universe is a realm of perpetual mystery, where every answer births new questions, and where the search for truth is as boundless as the stars themselves. In the vast, shimmering expanse of the cosmos, galaxies wheel in silent majesty, their spirals unfurling like celestial ribbons against the velvet night. For centuries, humanity has marveled at these luminous islands of stars, their movements governed by the invisible threads of gravity. Yet, within this grand cosmic dance lies a paradox, one that defies the very laws Isaac Newton etched into the fabric of classical physics. If we peer closely at the rotational speeds of galaxies, we uncover a mystery that has haunted astronomers and physicists alike. Why do stars at the outer edges of galaxies not fling themselves into the void, as Newton's equations would predict? Why do they instead orbit at velocities that suggest an unseen force is holding them in place? This anomaly, subtle yet profound, is not merely a curiosity of astrophysics. It is a revelation, a whisper from the universe itself, beckoning us to reconsider the limits of our understanding. The stars are not dancing to Newton's tune alone. They are swaying to an invisible rhythm, a symphony composed by an unknown hand, one that may rewrite the rules of existence. The universe, in its infinite complexity, often hides its secrets behind layers of apparent simplicity. Newton's law of universal gravitation, a cornerstone of scientific thought for over 3 centuries, describes how massive objects attract one another with a force proportional to their masses and inversely proportional to the square of the distance between them. According to this elegant framework, the stars in a spiral galaxy should behave much like planets in our solar system. Just as Jupiter orbits the Sun faster than Neptune does, the stars closer to a galaxy's core should move more rapidly than those at its periphery. Yet, when we observe these distant stellar systems, we find precisely the opposite. The outermost stars hurtle through space at velocities that should, by all rights, shatter the galaxy apart. This defiance of expectation is not a minor quirk, but a fundamental challenge to the foundations of physics. It is as if the cosmos has conspired to mislead us, hiding an enigma beneath the surface of its radiant beauty. To grasp the magnitude of this conundrum, imagine standing on a cliff overlooking a vast ocean. Below you, waves crash in rhythmic patterns, their motion seemingly predictable. But as you watch, you notice something peculiar. The waves nearest the shore rise and fall in harmony with the tides, while those farther out defy the pattern entirely, cresting with unrelenting vigor. You might assume there is an unseen current beneath the surface, an invisible force altering the ocean's behavior. Similarly, the universe's galaxies reveal an unseen current, an invisible ocean of mass that governs their motion. This hidden realm, neither light nor ordinary matter, remains undetected by our telescopes and instruments, yet its gravitational influence is undeniable. The realization that the visible universe is but a fraction of a vaster, unseen reality is humbling. It compels us to confront the possibility that our understanding of the cosmos is incomplete, that the laws we revere may require revision to accommodate the universe's deeper truths. The seeds of this cosmic riddle were sown in the mid-20th century, when astronomer Vera Rubin began meticulously mapping the rotational speeds of spiral galaxies. Her work, conducted alongside collaborator Kent Ford, unveiled a pattern that contradicted every expectation derived from Newtonian dynamics. In a typical galaxy, the orbital velocity of stars should decrease with increasing distance from the galactic center, mirroring the way planets orbit the Sun. However, Rubin's data revealed a startling uniformity. Stars in the outer regions of galaxies moved at nearly the same speed as those near the core. This flatness in the rotation curve, a term now synonymous with a dark matter problem, defied explanation. If Newton's laws held true, these stars should have long since escaped into the intergalactic void. Instead, they clung stubbornly to their orbits, as though bound by an invisible hand. To understand the gravity of this discovery, consider a simple analogy. Imagine a spinning merry-go-round, where children seated closer to the center whirl around faster than those on the outer edge. This is precisely what Newton's laws predict. The gravitational pull of the central mass accelerates objects in tighter orbits. Now picture a merry-go-round where every child, regardless of position, spins at the same dizzying speed. Such a scenario would demand an additional, unseen mass distributed evenly throughout the structure, providing the extra gravitational glue needed to prevent the outer riders from flying off. In the case of galaxies, this hypothetical mass must be immense, far greater than the visible stars, gas and dust combined. Astronomers calculated that galaxies contain roughly 5 to 10 times more mass than what is observable, hidden in an expansive halo surrounding each galaxy. This missing mass, dubbed dark matter, exerts no discernible influence on light or radiation, yet its gravitational effects are unmistakable. Rubin's findings, published in the 1970s, sent shockwaves through the astrophysical community. For decades, scientists had assumed that galaxies were self-contained systems, their visible components sufficient to account for their stability. The discovery of flat rotation curves shattered this assumption, revealing a cosmic scaffolding that remained invisible to even the most advanced telescopes. Further evidence emerged from studies of gravitational lensing, where the bending of light from distant quasars indicated the presence of unseen mass distorting space-time. Additionally, the cosmic microwave background, the relic radiation from the early universe, showed density fluctuations that could only be explained by the gravitational tug of dark matter. Together, these observations painted a picture of a universe where ordinary matter constitutes less than 5% of the total mass energy content, with dark matter and dark energy making up the remainder. Yet for all its explanatory power, dark matter remains one of the greatest enigmas in modern science. Unlike the familiar matter that forms stars, planets, and people, dark matter does not interact with electromagnetic forces, rendering it undetectable by traditional means. Its existence is inferred solely through its gravitational influence, a ghostly presence that shapes the cosmos from the shadows. Physicists have proposed numerous candidates for dark matter, from weakly interacting massive particles, WIMPs, to primordial black holes, yet none have been conclusively identified. Experiments such as the Large Underground Xenon Lux detector and the Alpha Magnetic Spectrometer, AMS, on the International Space Station continue the search for direct evidence. But the elusive nature of dark matter persists. In this context, the defiance of Newton's laws becomes not just a curiosity, but a profound challenge, one that compels us to rethink the fundamental architecture of the universe. The implications of this cosmic conundrum extend far beyond the rotation curves of galaxies. They touch upon the very nature of reality, the limits of human knowledge, and the possibility that our understanding of the universe is built on incomplete foundations. If dark matter is real, it suggests that the visible universe is but a small fragment of a vaster, unseen reality. The stars, nebulae, and planets we see are like the tip of an iceberg, floating atop an ocean of invisible mass. This revelation reshapes our perception of the cosmos, transforming it from a collection of luminous objects into a complex tapestry woven by forces we cannot yet comprehend. Moreover, it raises questions about the role of dark matter in the formation and evolution of galaxies. Without its gravitational scaffolding, the Milky Way, and perhaps all galaxies, might never have coalesced from the primordial chaos of the early universe. The absence of dark matter would leave the cosmos a barren expanse, devoid of the structures that give it form and meaning. Yet the dark matter hypothesis is not without its critics. Some physicists argue that rather than invoking an unseen substance, we should reconsider the fundamental laws of gravity themselves. The theory of modified Newtonian dynamics, MOND, proposed by Mordechai Milgrom in the 1980s, posits that Newton's laws break down at extremely low accelerations, such as those found in the outer reaches of galaxies. According to MOND, the gravitational force does not diminish as rapidly as predicted by Newtonian physics, allowing stars to remain in stable orbits without the need for dark matter. While MOND successfully explains the flatness of rotation curves in some cases, it struggles to account for other phenomena, such as the distribution of mass in galaxy clusters and the large-scale structure of the universe. Nevertheless, its existence highlights a critical point. The discrepancy between observation and theory may signal not a missing ingredient, but a flaw in our current understanding of gravity. The debate between dark matter and modified gravity reflects a deeper tension in science, the balance between extending known theories and proposing entirely new frameworks. On one side, dark matter offers a straightforward explanation that aligns with the broader successes of general relativity and the standard model of cosmology. On the other, MOND and its successors challenge the universality of Newton's laws, suggesting that our understanding of gravity may require refinement at cosmic scales. Both approaches underscore the provisional nature of scientific knowledge, reminding us that the universe may yet hold surprises that defy our expectations. As experimental techniques advance, future observations of dwarf galaxies, gravitational lensing, and the cosmic microwave background may tip the scales toward one interpretation or the other. Until then, the question of whether dark matter exists or whether gravity behaves differently on galactic scales remains one of the most profound open problems in astrophysics. Beyond the specifics of dark matter or modified gravity, the defiance of Newton's laws in galaxies invites us to reconsider the nature of scientific inquiry itself. For centuries, Newton's equations have served as the bedrock of physics, describing everything from the fall of an apple to the orbits of planets. Their success has led many to view them as immutable truths, etched into the fabric of reality. Yet the universe is not a static construct but a dynamic, evolving entity, and our models must adapt to its complexities. The fact that galaxies do not conform to Newtonian predictions is a reminder that the cosmos operates on principles that may lie beyond our current comprehension. It is a humbling acknowledgement that even our most cherished theories are subject to revision in the face of new evidence. This humility is essential as we grapple with the implications of the cosmic conundrum. If dark matter is indeed the correct explanation, it represents a triumph of inference over direct observation, a testament to the power of indirect reasoning in science. The ability to deduce the existence of an unseen substance based on its gravitational effects is a remarkable feat of human ingenuity. Conversely, if modified gravity proves to be the solution, it would mark a paradigm shift akin to Einstein's revolutionizing of Newtonian physics with general relativity. Either outcome would reshape our understanding of the universe, demonstrating that the cosmos is far more intricate than we ever imagined. In either case, the defiance of Newton's laws serves as a beacon, guiding us toward deeper truths hidden within the fabric of space-time. As we stand at the precipice of this cosmic mystery, the gravitational anomalies that define the rotation of galaxies ripple outward, threading the vast tapestry of the universe. These invisible currents, whether born of dark matter or a reimagined theory of gravity, do not act in isolation. They weave a grand design across the cosmos, connecting galaxies into sprawling networks and giving rise to structures that defy comprehension. Among these cosmic formations lies a phenomenon that exemplifies the far-reaching influence of gravity, the Great Attractor. Nestled deep within the southern sky, obscured by the dense veils of the Milky Way, the Great Attractor is a gravitational behemoth, a region of space whose unseen pull draws entire galaxies toward it with relentless determination. It is here, in the shadow of this enigmatic force, that we begin to glimpse the next chapter of our journey, a story of cosmic tides and the unseen forces that shape the destiny of the universe. The Great Attractor is not a single object, but a convergence of mass, so immense that it bends the trajectories of galaxies millions of light years away. Its gravitational influence is akin to a cosmic tide, a wave of unseen energy that stirs the heavens and compels celestial bodies to move in directions they would otherwise resist. As we turn our gaze toward this mysterious region, we are reminded that the universe is not a static expanse, but a living, breathing entity shaped by forces both seen and unseen. The defiance of Newton's laws in the rotation of galaxies is but one thread in this intricate web of cosmic interactions, a clue pointing toward a deeper understanding of the universe's structure and evolution. With this in mind, let us follow the pull of the Great Attractor, venturing into the heart of a cosmic enigma that continues to challenge and inspire our quest for knowledge. Above us, the Milky Way sprawls across the night sky, a luminous river of stars winding through the heavens. Yet beneath this familiar tapestry lies a secret, one that whispers of an invisible force, a silent tug dragging our galaxy through the void. This force is neither the wind of stellar radiation, nor the pulse of magnetic fields. It is the gravitational embrace of a colossal, unseen entity known as the Great Attractor, hidden behind the dense veil of the Milky Way's own stars and interstellar dust. This enigmatic region exerts a gravitational pull so immense that it draws our local group of galaxies toward it at a staggering speed of 600 kilometers per second. To comprehend this phenomenon is to confront the limits of our cosmic vision, to grapple with the idea that the universe may be shaped not only by what we see but by the shadows that loom beyond our sight. The Great Attractor is no mere anomaly. It is a testament to the universe's intricate balance of light and dark. While the visible cosmos dazzles with the brilliance of stars, nebulae, and galaxies, the hidden scaffolding of dark matter underpins it all. This invisible substance, which neither emits nor absorbs light, binds the cosmos together through its gravitational grip. It is dark matter that amplifies the Great Attractor's pull, transforming it from a distant curiosity into a cosmic linchpin. Yet, even as we trace the ripples of its influence across the fabric of space-time, the Great Attractor itself remains veiled, a phantom lurking in the zone of avoidance. The region of the sky, where the Milky Way's own brightness blinds our instruments. To speak of the Great Attractor is to speak of the universe's quiet poetry, the way matter clumps into vast superclusters, the way gravity carves highways through the cosmic ocean, and the way unseen forces choreograph the dance of galaxies. It is a reminder that the cosmos is not a static stage, but a living, breathing entity. Millions of light years to ensnare entire groups of galaxies in its orbit. But how do we know of its existence when it is obscured by the very stars of our own galaxy? The answer lies in the motion of celestial objects. By measuring the redshifts of galaxies in the local group, those that include the Milky Way, Andromeda, and their neighbors, scientists have detected a peculiar velocity, a movement not aligned with the general expansion of the universe, but instead directed toward a specific point in the sky. This motion suggests the presence of a massive gravitational sink, one whose pull is strong enough to counteract the universe's outward drift. However, because the Great Attractor lies within the zone of avoidance, a region of the sky blocked by the Milky Way's dense interstellar medium, traditional optical telescopes cannot pierce the veil. Instead, astronomers rely on indirect methods, such as mapping the distribution of galaxies in the infrared and X-ray wavelengths, to chart the unseen architecture of this cosmic behemoth. What makes the Great Attractor so extraordinary is not just its mass, but the role it plays in the larger cosmic ecosystem. Galaxies are not randomly scattered through space. They are organized into filaments and voids, forming a vast web-like structure known as the cosmic web. Within this web, superclusters act as gravitational anchors, their immense mass drawing neighboring galaxies into their orbits. The Great Attractor, however, stands apart. Its gravitational influence is so pronounced that it has created a sort of cosmic tide, a slow, inexorable flow of matter that sweeps galaxies toward it like water drawn into a whirlpool. This phenomenon challenges our understanding of gravity on cosmological scales, revealing that the universe is not a smooth, uniform expanse, but a dynamic, uneven terrain shaped by invisible forces. At the heart of this gravitational drama lies dark matter. Though we cannot see it, we can feel its presence. The mass required to account for the Great Attractor's pull far exceeds the visible matter in the region, suggesting that dark matter forms an invisible scaffold, amplifying the gravitational field and binding the supercluster together. Without dark matter, the Great Attractor would lack the heft to dominate the motion of galaxies. Instead, it is the unseen that holds sway, a reminder that the universe is governed by forces we cannot yet fully grasp. This interplay between visible and invisible matter raises profound questions. If dark matter is the architect of the Great Attractor's power, what other structures might it be shaping beyond our sight? Could there be other attractors, hidden in the blind spots of our observations, each exerting its own gravitational dominion? These questions underscore the limitations of our current tools and the humility required to navigate the cosmos. The Great Attractor is not just a destination for our galaxy, it is a mirror reflecting the vastness of what remains unknown. The discovery of the Great Attractor has reshaped our understanding of the universe's structure, exposing the fragility of our cosmic maps. For decades, astronomers believed the universe was isotropic, uniform in all directions on the largest scales. But the Great Attractor, along with other superstructures like the Shapley supercluster and the Hercules Corona Borealis Great Wall, reveals a cosmos teeming with asymmetry. These massive concentrations of matter disrupt the notion of a smooth, homogeneous universe, replacing it with a patchwork of density fluctuations where gravity reigns supreme. One of the most striking implications of the Great Attractor is its challenge to the Copernican principle, the idea that Earth occupies no special place in the cosmos. If our galaxy is hurtling toward this unseen force, does it mean we are in a privileged location, caught in the gravitational embrace of a local giant? Or is the Great Attractor merely one node in a network of similar attractors, each pulling at different regions of the universe? Recent simulations suggest the latter, that the universe may be a hierarchy of structures, with superclusters and voids forming a self-similar pattern across vast distances. Yet without direct observations of the Great Attractor's full extent, such conclusions remain speculative. The role of dark matter in these cosmic dynamics is equally enigmatic. While it accounts for roughly 85% of the universe's mass, its properties remain elusive. Unlike ordinary matter, dark matter does not interact via electromagnetic forces, meaning it cannot collapse into stars or galaxies. Instead, it forms halos around visible structures, providing the gravitational glue that holds them together. In the case of the Great Attractor, dark matter likely extends far beyond the visible supercluster, creating a diffuse invisible shell that enhances its gravitational pull. This suggests that the Great Attractor is not a discrete object, but a region where dark matter's density peaks, drawing galaxies into a slow spiral of convergence. Such revelations force us to reconsider the nature of motion in the universe. The Milky Way's journey toward the Great Attractor is not a chaotic stumble, but part of a grander design. Like a leaf carried by a river's current, our galaxy is swept along by the gravitational tides of the cosmic web. These tides are not static. They evolve over billions of years as structures grow and merge. The Great Attractor itself may eventually collide with the Shapley supercluster, creating a new gravitational behemoth that will reshape the motion of galaxies across the southern hemisphere of the sky. In this ever-changing landscape, Even the most massive attractors are transient, their influence waxing and waning as the universe expands. Yet the deeper mystery lies in the possibility of other attractors lurking beyond our sight. The zone of avoidance, with its dense veil of stars and gas, is not the only blind spot in our observations. Much of the universe remains uncharted, its structure inferred rather than seen. What if the Great Attractor is just one of many such gravitational anchors, each hidden in the shadows of cosmic dust or the limitations of our technology? The thought is humbling that we who pride ourselves on mapping the stars may still be blind to the forces that shape our galactic destiny. Moreover, the existence of attractors like the Great Attractor underscores the interconnectedness of the cosmos. Every galaxy, every star, every speck of dark matter is part of a vast interwoven system where motion is not random but purposeful. Our Milky Way's trajectory is not an isolated event, but a thread in the tapestry of the universe's evolution. As we trace the gravitational currents that guide our galaxy, we begin to see ourselves not as solitary travelers, but as marionettes dancing to the strings of unseen forces. This realization invites a sense of wonder and perhaps a touch of unease. If the Great Attractor's pull is so powerful that it can bend the paths of galaxies, what else might it reveal about the universe's hidden mechanisms? Could there be a universal rhythm to these gravitational tides? A cosmic heartbeat that pulses through the void? Or are we merely passengers in a ship adrift, unable to steer but destined to follow the course etched by dark matter's hand? Such questions have no easy answers, but they remind us that the universe is not a cold, indifferent expanse. It is a living entity, its secrets waiting to be uncovered. To unravel the mysteries of the Great Attractor and its unseen companions, we must turn our gaze inward, not to the stars above, but to the subatomic realm where dark matter may finally reveal its identity. For all its gravitational dominance, dark matter remains an enigma, a ghostly presence that neither shines nor interacts with light. Yet it is this very elusiveness that has driven humanity to seek it out, to build instruments capable of detecting the faintest whispers of its existence. If the Great Attractor is a monument to dark matter's power, then the quest to find its constituent particles is the key to deciphering its legacy. In laboratories buried deep beneath mountains and oceans, scientists have constructed detectors designed to catch the fleeting collisions of dark matter particles with ordinary matter. These experiments, operating in extreme conditions of isolation and silence, hope to capture the faintest flicker of energy that would betray the presence of dark matter's hypothetical constituents. WIMPs, weakly interacting massive particles, or Axions. Meanwhile, particle accelerators like the Large Hadron Collider attempt to recreate the conditions of the early universe, searching for signs that dark matter particles can be produced in controlled environments. The journey from the cosmic scale of the Great Attractor to the quantum scale of particle physics is one of extremes, yet it is bound by a shared pursuit to understand the invisible forces that govern the universe. Just as the Great Attractor reveals the power of dark matter on a galactic scale, the experiments in our labs may soon unveil its fundamental nature. With each collision, each measurement, we edge closer to bridging the gap between the vast and the minute, between the cosmic tides and the tiniest particles of existence. In the vast, silent expanse of the universe, where galaxies spiral in elegant dances and stars burn with ancient light, there exists an enigma that defies comprehension. Dark matter, the invisible scaffolding of the cosmos, remains one of the most profound mysteries humanity has ever confronted. Though unseen, its gravitational pull shapes the orbits of galaxies, binds clusters of galaxies together, and seeds the large-scale structure of the universe. Yet for all its influence, dark matter remains an ephemeral ghost, eluding direct detection. Scientists, armed with ingenuity and instruments honed to the limits of human technology, now turn their gaze inward, probing the quantum realm for answers. Among the candidates for this cosmic riddle are two particularly intriguing possibilities: weakly interacting massive particles, WIMPs and Axions. These hypothetical entities, born from the interplay of particle physics and cosmology, represent humanity's best hope to unravel the nature of the dark sector. The hunt for these particles is not merely a scientific endeavor, it is a pilgrimage into the unknown, a quest to decipher the silent whispers of a universe that has remained stubbornly, tantalizingly opaque. As detectors hum in deep underground laboratories and telescopes scan the void for faint anomalies, the scientific community braces itself for a revelation, or perhaps a humbling re-evaluation of its understanding of reality itself. To grasp the significance of WIMPs and Axions, one must first navigate the intricate web of theoretical physics that birthed them. At its core, the search for dark matter hinges on reconciling observations with the standard model of particle physics, which, despite its triumphs, leaves critical questions unanswered. The standard model describes the fundamental particles and forces governing the visible universe. Yet it accounts for less than 5% of the cosmos's total mass energy content. The remaining 95% dark matter and dark energy resides in a shadowy domain beyond its reach. WIMPs, as their name suggests, are particles that interact feebly with ordinary matter. They are hypothesized to possess masses ranging from a few giga-electron-volts, GeV, to hundreds of GeV, placing them far heavier than familiar particles like electrons or quarks. Crucially, WIMPs interact via gravity and the weak nuclear force, the latter responsible for processes such as radioactive decay. This duality grants them a unique property. While their gravitational pull anchors them to galaxies, their weak interactions render them nearly invisible to electromagnetic detection. If WIMPs exist, they would have been produced in abundance during the early universe, streaming through space like a cosmic fog. Detecting them requires capturing the rare fleeting collisions between WIMPs and nuclei in highly sensitive detectors. Experiments such as LUX, Large Underground Xenon, and Xenon employ liquid xenon, a material chosen for its high atomic number and ability to amplify faint signals. When a WIMP collides with a xenon nucleus, it should produce a minuscule flash of light and a phonon, a quantum of vibrational energy that experimentalists painstakingly measure. The challenge lies in distinguishing these hypothetical events from background noise caused by cosmic rays and radioactive decay. To mitigate this, detectors are often buried deep underground, shielded by kilometers of rock that filter out most ambient radiation. Axions, by contrast, emerge from a different branch of physics, proposed in the 1970s to resolve a perplexing symmetry issue in quantum chromodynamics, QCD. The theory of the strong nuclear force. Axions are ultralight particles, potentially millions of times lighter than an electron. Unlike WIMPs, which are envisioned as heavy relics of the Big Bang, axions are theorized to arise from a dynamic field that permeates the universe. Their extreme lightness allows them to exhibit wave-like behavior on cosmological scales, oscillating in harmony with the fabric of space-time. Detecting axions is a feat of precision engineering. The Axion dark matter experiment, ADMX for instance, uses a powerful magnetic field to convert axions into photons within a resonant cavity. If axions exist, their oscillations should generate a faint electromagnetic signal at a frequency determined by their mass. By tuning the cavity and scanning a range of frequencies, ADMX aims to capture this spectral echo of the dark sector. The experiment operates in a vacuum at temperatures near absolute zero to minimize thermal interference, a testament to the razor-thin margin between detection and noise. These dual approaches, hunting WIMPs through direct collisions and axions through their electromagnetic signatures, represent complementary strategies in the broader quest for dark matter. Both rely on the principle that even the faintest interaction can, under the right conditions, be amplified into a measurable signal. Yet for all their sophistication, these experiments remain constrained by the limits of current technology. The absence of a definitive detection thus far underscores the daunting scale of the challenge. To find a needle in a haystack where the needle may not exist, should WIMPs or axions be discovered, the ramifications would ripple across the foundations of modern physics. A detection of WIMPs would validate a cornerstone of supersymmetry, a theoretical framework that extends the standard model by introducing partner particles for every known fermion. Supersymmetry not only provides a natural candidate for dark matter, but also addresses other unresolved issues, such as the hierarchy problem, the puzzling disparity between the Higgs boson's mass and the Planck scale. Moreover, WIMPs would serve as a bridge between particle physics and cosmology, offering insights into the universe's evolution from the hot Big Bang to its present-day structure. Similarly, the discovery of Axions would resolve the QCD strong CP problem, a decades-old conundrum concerning the absence of observable electric dipole moments in neutrons. Beyond their immediate theoretical significance, Axions could explain the observed distribution of dark matter halos, as their wave-like properties might suppress small-scale structures. Aligning with astrophysical data, either outcome would cement the existence of the dark sector as a tangible extension of our physical laws, transforming it from an abstract necessity into a quantifiable reality. Yet, the absence of a detection is equally profound. If WIMPs and Axions remain undetected, despite increasingly sensitive experiments, it would compel physicists to reconsider their assumptions. One alternative is the sterile neutrino, a hypothetical particle that interacts solely via gravity. Sterile neutrinos, if they exist, could account for dark matter while explaining anomalies in neutrino oscillation experiments. Another possibility lies in primordial black holes, which could have formed in the early universe from density fluctuations, while indirect evidence for such objects exists in gravitational wave observations. Their viability as dark matter candidates hinges on their mass distribution and abundance. More radically, some theorists propose that dark matter may not be composed of particles at all, but instead arises from modifications to gravity itself. Theories like modified Newtonian dynamics, MOND, suggest that Einstein's equations break down on galactic scales, obviating the need for unseen mass. Though controversial, MOND and its relativistic extensions, e.g. TeVs, continue to spark debate, challenging the paradigm that dark matter must be a form of exotic particle. The implications extend beyond particle physics. A failure to detect WIMPs or Axions would underscore the limitations of human knowledge and the fallibility of even the most promising hypotheses. It would also highlight the interconnectedness of scientific inquiry, where the pursuit of one mystery often illuminates others. For example, the search for Axions has advanced technologies in cryogenics and superconductivity, while WIMP experiments have refined techniques for detecting rare nuclear recoils. These spin-off applications, though secondary to the primary goal, demonstrate that the value of scientific exploration lies not only in its outcomes, but also in the tools it forges. More broadly, the hunt for dark particles reflects a deeper philosophical truth. The universe resists easy answers. Its complexity demands humility, reminding us that our current models, however elegant, are provisional. Consider the history of physics. The Michelson-Morley experiment's failure to detect the luminiferous aether led to Einstein's theory of relativity. The anomalous precession of Mercury's orbit hinted at general relativity's necessity. In both cases, the absence of expected results catalyzed revolutionary breakthroughs. Could the same be true for dark matter? Perhaps the missing piece lies not in refining existing theories, but in reimagining the very framework through which we perceive reality. As the search for dark matter continues to unfold, another enigma looms on the horizon: dark energy. While dark matter clings to galaxies like an unseen glue, dark energy drives the accelerating expansion of the universe, a phenomenon first observed in 1998 through measurements of distant supernovae. Together, these two cosmic entities, dark matter and dark energy, comprise the vast majority of the universe's mass-energy budget, yet their natures remain shrouded in mystery. Just as WIMPs and Axions represent competing explanations for dark matter, dark energy harbors its own array of possibilities, chief among them the concept of phantom energy. Unlike the cosmological constant proposed by Einstein, which posits a static, unchanging energy density, phantom energy implies a negative pressure so intense that it could ultimately tear apart galaxies, stars, and even atoms in a cataclysmic event known as the Big Rip. This stark contrast between dark matter and dark energy invites a profound reflection on the universe's duality. Where dark matter binds, dark energy repels. Where one seeks to anchor structure, the other propels its dissolution. Yet both share a common trait. They are phenomena revealed not through direct observation, but through their gravitational effects. In the next segment, we will delve into the shadowy cousin of dark matter, phantom energy, and explore its implications for the ultimate fate of the cosmos. For now, as we stand at the crossroads of discovery and uncertainty, the universe offers no answers, only questions, a reminder that the greatest revelations often lie just beyond the edge of perception. In the vast, silent expanse of the universe, two invisible titans clash in a battle that has raged for billions of years. One is the unseen hand that binds galaxies into grand cosmic webs, holding the fabric of the cosmos together. The other is the mysterious force that drives those same galaxies apart, stretching the universe toward an uncertain future. These two enigmas, dark matter and dark energy, comprise nearly 95% of all that exists, yet their true natures remain shrouded in mystery. Together, they dictate the ultimate fate of the cosmos, locked in an eternal struggle between cohesion and dissolution. To understand this cosmic duel is to peer into the deepest questions of existence. What holds the universe together? What tears it apart? And who or what will emerge victorious in this celestial game of balance? The story begins with a realization that the visible universe, the stars, planets, gas clouds, and galaxies we observe, is but a fleeting whisper in the grand symphony of creation. Ordinary matter, the stuff of which we are made, accounts for less than 5% of the universe's total mass energy content. The remaining 95% is composed of two elusive entities: dark matter, an invisible scaffold that gives structure to the cosmos, and dark energy, a phantom force that accelerates the universe's expansion. While dark matter acts as gravity's unseen glue, dark energy functions as an anti-gravity force, pushing galaxies away from one another at an ever-increasing pace. Their interplay shapes the past, present, and future of the universe. Yet their identities remain among the greatest unsolved puzzles in modern science. This debate is not merely academic. It is a profound exploration of the laws that govern reality itself. The tug-of-war between dark matter and dark energy transcends the boundaries of physics, touching on philosophy, cosmology, and even existential inquiry. If dark matter prevails, the universe may contract into a dense, fiery singularity, a big crunch, reversing the cosmic clock. If dark energy dominates, the universe will expand indefinitely, growing colder and emptier until all galaxies vanish beyond the reach of light in a big freeze. A more dramatic possibility, the Big Rip, envisions dark energy intensifying to such an extent that it unravels galaxies, stars, and even atoms themselves. The outcome hinges on the nature of these unseen forces, forces that defy our conventional understanding of matter and energy. As we embark on this journey through the cosmos, we are reminded of humanity's place in the grand scale of existence. We are but stardust adrift in an ocean of darkness, seeking to decipher the silent code written into the fabric of space-time. The phantom energy debate compels us to confront the limits of our knowledge and to marvel at the elegance of a universe that both defies and inspires. In the following pages, we will unravel the origins of dark matter and dark energy, dissect their properties, and explore the cosmic stakes of their eternal struggle. Along the way, we will glimpse the ingenuity of scientists who strive to map the invisible, to decode the whispers of a universe that has no voice but speaks through the dance of galaxies. To grasp the essence of dark matter and dark energy, we must first confront the limitations of our senses and instruments. These entities are not mere extensions of familiar physics. They are anomalies, deviations from the expected behavior of the cosmos that demand new frameworks of understanding. Dark matter, first proposed in the 1930s by Swiss astronomer Fritz Zwicky, emerged as a solution to a perplexing problem. Galaxy clusters appeared to contain far less mass than required to hold them together. Observations revealed that the gravitational pull binding these clusters exceeded the combined mass of their visible components, stars, gas, and dust, by a factor of 10. Zwicky postulated the existence of an unseen substance, which he termed dunkel materie, dark matter, to account for the missing mass. Decades later, Vera Rubin's groundbreaking work on galaxy rotation curves cemented this hypothesis. She found that stars in spiral galaxies orbit their cores at speeds inconsistent with the visible matter alone. If gravity obeyed Newtonian laws, outer stars should move more slowly, but instead they hurtled at velocities that implied the presence of an invisible halo of dark matter enveloping each galaxy. Dark matter is not a substance we can see, touch, or even directly detect. It does not emit, absorb, or reflect electromagnetic radiation, rendering it invisible to our telescopes. Its existence is inferred solely through its gravitational influence on visible matter. Theoretical models suggest that dark matter consists of non-baryonic particles, entities unlike protons, neutrons, or electrons, that interact with ordinary matter only through gravity and perhaps the weak nuclear force. Candidates for these particles range from hypothetical weakly interacting massive particles, WIMPs, to lighter axions, but none have been conclusively detected. Despite this, dark matter's role in shaping the universe is undeniable. Without it, galaxies would not form, and the large-scale structure of the cosmos, the web of filaments and voids that stretches across billions of light-years, would collapse into chaos. If dark matter is the architect of cosmic structure, dark energy is the architect of cosmic destiny. Discovered in 1998 through observations of distant Type 1a supernovae, dark energy revealed a shocking truth: the universe is not decelerating under the pull of gravity as previously assumed, but accelerating in its expansion. Two independent teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Riss, measured the light from these exploding stars and found that they were fainter and thus farther away than expected. This discrepancy indicated that the universe's expansion had sped up over time, driven by an unknown force. This force, dubbed dark energy, constitutes approximately 68% of the universe's total energy content. Unlike dark matter, which clumps and aggregates under gravity, dark energy appears to permeate all of space uniformly, exerting a repulsive gravitational effect that counteracts the pull of matter. The most straightforward explanation for dark energy comes from Albert Einstein's equations of general relativity. In 1917, Einstein introduced the cosmological constant, denoted by the Greek letter m, to his field equations as a way to stabilize the universe against collapse. When Edwin Hubble later proved that the universe was expanding, Einstein famously called the cosmological constant his greatest blunder. However, the discovery of cosmic acceleration resurrected the idea, suggesting that the cosmological constant represents a fixed energy density inherent to empty space itself. This interpretation aligns with quantum field theory, which predicts that the vacuum of space is not truly empty, but teeming with virtual particles and fluctuating energy fields. The challenge lies in reconciling the observed value of the cosmological constant with theoretical predictions which differ by an astronomical factor of 10^120, a discrepancy often referred to as the worst prediction in physics. An alternative to the cosmological constant is the concept of quintessence, a dynamic form of dark energy that varies over time and space. Unlike the static cosmological constant, quintessence posits a scalar field similar to the Higgs field, whose energy density evolves as the universe expands. This model offers flexibility in explaining cosmic acceleration, but requires the introduction of new physical laws and particles. Theorists continue to debate whether dark energy is a constant feature of the universe or a transient phenomenon, with ongoing experiments such as the Dark Energy Survey and the Euclid mission striving to measure its properties with greater precision. The interplay between dark matter and dark energy defines the universe's evolutionary path. Today, dark energy makes up roughly 2/3 of the cosmos, while dark matter accounts for about a quarter, with ordinary matter comprising a mere sliver. Over the next few billion years, dark energy's dominance will grow, driving galaxies further apart until they fade from view. This accelerating expansion challenges our understanding of time, space, and causality, forcing us to reimagine the universe as a dynamic entity shaped not only by matter, but by the very fabric of space-time itself. The balance between dark matter and dark energy is not merely a question of numbers, It is a determinant of the universe's ultimate fate. Current observations suggest that dark energy will continue to dominate, propelling the universe into an era of exponential expansion. However, the exact trajectory of this expansion depends critically on the nature of dark energy. Is it a fixed constant, as Einstein envisioned, or a dynamic force that evolves over time? The answer will decide whether the universe meets a cold, lonely end or undergoes a cataclysmic unraveling. One of the most widely accepted scenarios is the Big Freeze, also known as the heat death of the universe. In this model, dark energy remains constant, causing galaxies to recede from one another at an accelerating rate. Over trillions of years, the distances between galaxies will stretch so far that their light becomes redshifted beyond detection, leaving the observable universe isolated and barren. Stars will exhaust their fuel, black holes will evaporate via Hawking radiation, and the cosmos will settle into a state of maximum entropy, a frigid, static expanse where no meaningful processes occur. The Big Freeze is a sobering vision, a universe that outlives itself in silence, its once vibrant tapestry reduced to a monochrome void. Yet, if dark energy behaves differently, the universe could face an even more dramatic demise, the Big Rip. In this scenario, dark energy's repulsive force grows stronger over time, eventually overcoming the gravitational pull that binds galaxies, stars, and even atoms. The acceleration of the universe's expansion would escalate to the point where the fabric of space-time itself tears apart, disintegrating matter at every level of organization. The Milky Way would dissolve before the Sun, Earth, and ultimately subatomic particles meet their end. The Big Rip is not just an end of the universe, it is an end of everything, a finality so absolute that it defies comprehension. These scenarios highlight the precarious equilibrium between dark matter and dark energy. If dark energy was slightly weaker, the universe might collapse in a big crunch, reversing the Big Bang in a fiery implosion. If it was stronger, the Big Rip becomes inevitable. The fact that dark energy's strength appears finely tuned to allow life to exist, neither too strong to prevent galaxy formation, nor too weak to cause premature collapse, raises profound questions about the nature of the cosmos. Is this balance a cosmic coincidence? Or is it the result of deeper principles yet to be uncovered? Beyond the question of the universe's fate lies a more fundamental inquiry. What is the relationship between dark matter and dark energy? Are they distinct phenomena, or do they share a common origin? Some theories propose that dark matter and dark energy are two faces of a single, unified force. For instance, modified gravity models, such as T-Vismai's tensor vector scalar gravity and MOG modified gravity, suggest that the apparent effects of dark matter and dark energy arise from subtle alterations to Einstein's equations, rather than the existence of new particles. These models challenge the standard LNCDM, nice lambda cold dark matter, paradigm, offering alternative explanations for galactic dynamics and cosmic acceleration. Another line of inquiry explores the possibility that dark matter interacts with dark energy in ways we have yet to discover. Could dark matter particles decay into dark energy over time, transferring mass into energy and altering the balance of forces? Or might dark energy influence the distribution of dark matter, creating feedback loops that shape the universe's structure? These questions remain unanswered, but their pursuit underscores the interconnectedness of cosmic phenomena. The universe is not a collection of isolated entities, but a web of relationships, where the behavior of one component reverberates through the others. The search for answers has driven scientists to push the boundaries of observation and theory. Experiments like the Large Hadron Collider seek to detect dark matter particles by recreating conditions akin to the early universe, while space telescopes such as the James Webb Space Telescope probe the faint glow of the cosmic microwave background to trace the imprint of dark energy. On the theoretical front, physicists are developing new mathematical frameworks to reconcile general relativity with quantum mechanics, hoping to uncover a unified theory that explains both dark matter and dark energy. Yet for all our technological advancements and intellectual rigor, the universe continues to resist easy categorization. The more we learn, the more we realize how much remains unknown. The phantom energy debate is a testament to the humility of science. a reminder that the cosmos is a vast, intricate puzzle, and each piece we uncover reveals new layers of complexity. In this endless quest for understanding, we are not merely observers of the universe. We are participants in its unfolding story, forever striving to bridge the gap between the seen and the unseen, the known and the infinite. As we stand on the precipice of this cosmic enigma, the next step in our journey demands a shift in perspective, from the abstract to the tangible, from theory to observation, to unravel the mysteries of dark matter and dark energy. Scientists must navigate the invisible, crafting tools and techniques to detect forces that neither emit light nor conform to familiar patterns. This endeavor is not merely a technical challenge, it is a testament to human ingenuity, a dance between imagination and precision. How do we chart a universe that resists visibility? How do we measure what cannot be seen? The answer lies in indirect methods, in the echoes left behind by the unseen. In the coming segment, we will delve into the cutting-edge technologies and ingenious strategies employed by astrophysicists to map the invisible. From the subtle distortions of light caused by gravitational lensing to the faint ripples in the cosmic microwave background, each clue is a thread in the tapestry of the cosmos. We will explore how simulations reconstruct the distribution of dark matter across the universe, and how particle detectors scan for the ghostly signatures of WIMPs or Axions. Through these efforts, we inch closer to a comprehensive picture of the universe, one that transcends the limitations of sight and embraces the full spectrum of existence. The next chapter is not just about data and equations. It is about the relentless curiosity that drives humanity to seek meaning in the void. As we prepare to unveil the unseen, we are reminded that the universe, in all its invisibility, is not a riddle without an answer, but a canvas waiting for the strokes of discovery. In the vast expanse of the universe, where stars burn like distant embers and galaxies spiral in silent waltzes, lies a mystery far deeper than the voids between them. For centuries, humanity has gazed upward, piecing together the architecture of the cosmos from the faint glimmers of light. Yet, even as we chart the positions of billions of stars and decode the life cycles of galaxies, we remain blind to over 80% of the universe's mass, a shadowy substance known as dark matter. It does not emit, absorb, or reflect light, yet its gravitational grip binds galaxies together, shaping the cosmic web we observe. To understand this invisible scaffolding, scientists have turned to the most powerful tools at their disposal: supercomputers. These digital titans, capable of performing quadrillions of calculations per second, reconstruct the universe's dark side, tracing the evolution of dark matter from the fiery aftermath of the Big Bang to the present day. Through simulations, researchers peer into a hidden world, one governed by forces we cannot see but can infer. These virtual universes are not mere abstractions, they are tests of our deepest theories, battlegrounds, where the lambda CDM model of cosmology faces the raw data of reality. As we embark on this journey through simulated space, we confront not only the nature of dark matter, but the limits of human knowledge itself. What secrets lie buried in the code of these models? And what might they reveal about the unseen hand that shaped our existence? At the heart of modern cosmology lies a paradox. The universe is filled with matter we cannot see, yet its influence is everywhere. To map this invisible realm, scientists employ n-body simulations, mathematical models that track the motion of millions of particles under the pull of gravity. These simulations begin with the early universe, a time when density fluctuations in the cosmic microwave background, CMB, seeded the first ripples of structure. By inputting initial conditions derived from CMB observations, supercomputers evolve these perturbations forward in time, calculating how dark matter clumps and streams across eons. The result is a dynamic three-dimensional map of the cosmic web, filaments of dark matter stretching across billions of light years, punctuated by dense nodes where galaxies will eventually form. Among the most ambitious projects in this field are the Illustrist NG and Millennium simulations. The Millennium simulation, launched in 2005, was one of the first to model the distribution of dark matter on a cosmic scale, using a cubic volume of space 2 billion light-years on each side. Its successor, Illustrist NG, expanded this vision by incorporating not just dark matter but baryonic matter, the ordinary stuff of stars and gas, allowing researchers to study how dark matter's gravitational scaffolding shapes visible galaxies. These simulations rely on Newtonian gravity and hydrodynamics, solving equations of motion for trillions of particles with algorithms optimized for supercomputing clusters. Each simulation is a digital universe, a controlled experiment where variables such as the density of dark matter or the expansion rate of the cosmos can be adjusted to test theoretical predictions. But how do scientists determine if these simulations are accurate? The answer lies in observation. By comparing the simulated distribution of dark matter to real-world phenomena, such as the distribution of galaxy clusters or the bending of light in gravitational lensing, researchers calibrate their models. Gravitational lensing, in particular, acts as a natural telescope. The warped light from distant galaxies reveals the mass of intervening objects, much of which is dark matter. When the patterns of this warping align with the predictions of simulations, it reinforces the validity of the underlying physics. However, discrepancies arise, challenging assumptions. For instance, while simulations predict a certain number of small dark matter halos, observations reveal fewer satellite galaxies than expected. Such mismatches are not failures but invitations to refine our understanding, pushing the boundaries of both computation and theory. The lambda CDM model, the standard framework of cosmology, underpins these simulations. It posits that dark matter consists of cold particles, moving slowly enough to clump hierarchically, forming smaller structures before merging into larger ones. This model explains the large-scale structure of the universe remarkably well, yet its success raises new questions. Are the cold dark matter particles truly the final answer? Or do the gaps in simulation reality comparisons hint at a more complex picture? As supercomputers grow more powerful, capable of resolving finer details, the dialogue between theory and observation becomes ever sharper, illuminating both the strengths and weaknesses of our cosmic blueprint. The triumphs of dark matter simulations are undeniable. They have reproduced the grand architecture of the universe with uncanny precision, from the sprawling filaments of the cosmic web to the isolated voids where galaxies rarely form. The hierarchical clustering predicted by the lambda CDM model, where smaller dark matter halos merge to build larger ones, aligns with observations of galaxy distributions and the motions of stars within them. Yet for all their successes, these simulations also expose cracks in our understanding. Chief among these is the so-called missing satellites problem. While simulations predict thousands of small dark matter halos orbiting galaxies like the Milky Way, only a few hundred dwarf galaxies have been observed. This discrepancy suggests either that many of these halos lack sufficient gas to form stars, or that our assumptions about dark matter's behavior are incomplete. Another enigma arises in the too big to fail problem. Some of the most massive dark matter halos predicted by simulations are far denser than the observed satellite galaxies that should inhabit them. If dark matter is indeed cold and collisionless, as the lambda CDM model assumes, these halos should exist. Their absence implies that either the simulations are oversimplified or that additional astrophysical processes, such as feedback from supernovae or the heating of interstellar gas, are suppressing star formation in these regions. While such processes are now incorporated into advanced simulations like Illustrist NG, the tension between prediction and observation remains unresolved. Could this be a hint that dark matter is not entirely cold, but instead possesses a slight warmth, a gentle velocity that prevents the formation of the densest halos? Or might it interact with itself in ways not accounted for in current models? These questions ripple outward, challenging the very foundations of cosmology. The lambda CDM model, for all its elegance, is built on a minimalist assumption that dark matter is a single type of particle, non-interacting, except through gravity. But what if this assumption is too narrow? Alternative theories propose that dark matter could be warm, composed of faster-moving particles that smooth out small-scale structures. Others suggest that dark matter interacts via forces beyond gravity, perhaps through a hypothetical dark photon or through collisions that dissipate energy. These possibilities, though speculative, are not without merit. Recent studies of the Bullet Cluster, a system where two galaxy clusters collided, have revealed that dark matter passes through itself without scattering, supporting the cold dark matter hypothesis. Yet the same data cannot rule out rare interactions or subtle deviations from the standard model. The implications extend beyond dark matter itself. If the lambda CDM model falters, it could mean that our understanding of the universe's expansion, driven by dark energy, is also incomplete. The cosmic dance of dark matter and dark energy shapes the fate of the cosmos, yet both remain shrouded in mystery. Simulations offer a window into this interplay, revealing how dark energy's accelerating pull stretches the cosmic web over billions of years. However, discrepancies between simulations and observations of the universe's expansion rate, known as the Hubble tension, suggest that our models may still be missing critical components. Is there a hidden force at work, a modification to Einstein's theory of gravity, or perhaps an unknown form of matter that subtly alters the balance of cosmic forces? As we stand at this crossroads, the scientific community faces a profound choice. Should we cling to the lambda CDM model, refining its parameters to account for anomalies, or should we venture into uncharted territory, exploring alternatives that defy convention? The answer may lie in the next generation of simulations, which will incorporate not only higher resolution, but also novel physics, such as the effects of magnetic fields, the role of supermassive black holes, or the potential for dark matter to form complex structures. In parallel, experiments like the Large Hadron Collider and direct detection efforts in underground laboratories seek to uncover the true nature of dark matter particles. Yet, until these efforts yield definitive results, simulations remain our most powerful tool for probing the invisible. They remind us that the universe is a vast, intricate machine, whose gears turn with a logic we are only beginning to comprehend. Perhaps then, the greatest lesson of dark matter simulations is not in their answers, but in their questions. They reveal the limits of human ingenuity, the humility required to confront the unknown. When we run a simulation and find that the universe behaves differently than predicted, we are humbled by the realization that we are not its architects but its students. And yet, in this humility lies a spark of wonder. Every discrepancy, every anomaly, is an invitation to imagine further, to dream of a cosmos richer and stranger than we dare to suppose. For in the end, the search for dark matter is not merely a quest to fill in the blanks of our cosmic inventory. It is a journey toward understanding the very essence of existence, the forces that bind us, the voids that define us, and the infinite possibilities that lie beyond the edges of our vision. Yet for all the insights these simulations provide, they remain bound by the constraints of classical physics. They trace the gravitational ballet of dark matter particles across eons, but they cannot yet glimpse the subatomic realm where these particles might originate or interact. The lambda CDM model assumes that dark matter exists as a stable, collisionless substance, yet its true nature remains elusive. If we are to unravel the final threads of this cosmic puzzle, we must look beyond the macroscopic structures of the universe and into the quantum domain, a realm where particles behave not as solid entities, but as probabilities, where the rules of gravity give way to the strange symphony of quantum fields. Quantum physics offers tantalizing hints that the dark sector may not be as inert as once thought. Hypothetical particles, like Axions or sterile neutrinos, could mediate interactions between dark matter and ordinary matter, leaving faint imprints in experiments designed to detect them. Moreover, quantum entanglement and field theories suggest that dark matter might weave itself into the fabric of space-time in ways we have yet to grasp. These ideas are nascent, their implications vast. As we prepare to explore this quantum frontier, we enter a realm where the line between the known and the unknown dissolves, and where the universe's deepest secrets may whisper their truths in languages we have yet to learn. Let us now turn our gaze inward, from the cosmic web of dark matter to the quantum tapestry that may govern its existence. What lies beneath the surface of this invisible world? The next segment invites us to listen closely, for in the silence of the dark sector, the universe may be speaking. In the vast, star-studded expanse of the cosmos, there lies an enigma that has haunted humanity for generations, the dark sector. While visible matter, the stars, planets and galaxies we behold, accounts for only 5% of the universe's total mass energy content, the remaining 95% remains shrouded in mystery, split between dark matter and dark energy. Dark matter in particular acts as an invisible scaffold upon which galaxies form, its gravitational pull binding the cosmos together like an unseen architect. Yet despite its dominance, it eludes direct detection, revealing itself only through its gravitational fingerprints. Could this elusive substance, long dismissed as a mere shadow in the cosmic fabric, harbor secrets far beyond our comprehension? Emerging theories now whisper of a tantalizing possibility that dark matter might not be a passive, inert substance, but a dynamic realm governed by its own hidden laws. Some physicists propose that the dark sector mirrors our familiar universe, operating under parallel quantum principles. Imagine a shadow world, where particles dance in rhythms we cannot yet perceive, where forces ripple through hidden dimensions, and where the very act of observation might unlock a dialogue between realms. This notion challenges the boundaries of our understanding, suggesting that the dark sector is not a void, but a vibrant interconnected domain. The idea of a mirrored quantum reality raises profound questions. If dark matter communicates through quantum entanglement, a phenomenon Einstein famously called spooky action at a distance, does it transmit information across the cosmos in ways we've yet to decipher? Or might it dwell in extra dimensions, inaccessible to our senses, but detectable through indirect whispers in particle experiments? These hypotheses invite us to reimagine the universe not as a single static entity, but as a layered tapestry of interwoven worlds. As we peer into the abyss of the dark sector, we may find not emptiness, but a universe of unseen symphonies waiting to be heard. To unravel the mysteries of the dark sector, scientists have turned to the subatomic realm, where quantum mechanics reigns supreme. Among the most compelling candidates for bridging the gap between ordinary and dark matter are hypothetical particles known as dark photons and axion-like particles. Dark photons, analogous to the photons that mediate electromagnetic force in our universe, are theorized to interact weakly with visible matter. They could act as messengers, carrying signals between the two realms. Similarly, axion-like particles, hypothetically lightweight and electrically neutral, are proposed as carriers of a fifth force, one that might govern interactions within the dark sector. Experiments such as the Cosmic Axion Spin Precession Experiment, CASPER, are designed to detect these elusive entities by scrutinizing the behavior of atomic nuclei. The principle is deceptively simple. If axion-like particles exist, they would cause tiny oscillating torques on the spins of atomic nuclei, akin to a whisper distorting the rhythm of a pendulum. By measuring these minuscule fluctuations with exquisite precision, CASPER aims to catch the first glimmers of dark matter's hidden activity. Such efforts are painstaking, requiring instruments sensitive enough to detect changes smaller than the width of a proton. Yet, they represent humanity's audacious attempt to decode a language written in the quantum fabric of reality. Parallel to these endeavors, theories rooted in string theory and M-theory suggest that dark matter might inhabit extraspatial dimensions. According to these frameworks, our universe exists on a three-dimensional brane floating within a higher dimensional bulk. Dark matter, in this view, could seep into these additional dimensions, evading detection by our three-dimensional senses. This concept evokes a cosmic theater, where dark matter actors perform in unseen dimensions, their movements influencing the stage of our observable universe through subtle gravitational tugs. If confirmed, this would redefine our understanding of space itself, transforming it from a fixed backdrop into a dynamic, multi-dimensional canvas. Yet the path to discovery is fraught with uncertainty. Unlike the standard model particles that govern ordinary matter, dark sector entities remain stubbornly out of reach. Their interactions are so faint that even the most advanced detectors must sift through mountains of background noise to discern a signal. This challenge underscores the humbling truth. In our quest to understand the universe, we are both explorers and blindfolded cartographers, mapping landscapes we cannot yet see. If dark matter indeed possesses its own forces and particles, the implications ripple outward, reshaping our perception of reality. The universe may not be a singular, self-contained entity, but a mosaic of overlapping layers, each with its own set of physical laws. In this vision, our visible cosmos is but one sheet in a grander, multi-dimensional quilt, stitched together by the threads of quantum entanglement and hidden dimensions. Such a framework invites speculation about the nature of existence itself. Are we inhabitants of a single story in a cosmic epic, or characters in a tale written across countless parallel narratives? The idea of a dark sector with autonomous dynamics raises even more provocative questions. If dark matter can interact with itself through forces we do not yet understand, could it give rise to structures, patterns, or even forms of complexity comparable to those in our visible universe? Might there be dark stars, dark galaxies, or dark life forms thriving in the unseen expanse? These possibilities, though speculative, align with the principle of naturalism, that the laws governing our universe are not unique, but part of a broader universal code. If life arose from the interplay of matter and energy in our realm, could it similarly emerge from the quantum ballet of the dark sector? Such musings lead us to the most profound frontier of all, consciousness. Could the hidden forces of the dark sector influence the emergence of awareness in ways we cannot yet fathom? While mainstream science holds that consciousness arises from neural networks and biochemical processes, the dark sector's hypothetical autonomy suggests an alternative lens. If dark matter interacts with ordinary matter through quantum entanglement, might it subtly influence the delicate dance of particles within biological systems? Could the universe itself possess a form of distributed cognition, with dark matter serving as a substratum for collective memory or information processing? These ideas, though bordering on poetic speculation, challenge us to consider whether consciousness is not a singular phenomenon confined to Earth, but a property woven into the very fabric of the cosmos. Even if such notions remain unproven, they underscore a humbling truth. Our understanding of reality is fragmentary. The dark sector, with its potential for hidden dimensions and parallel forces, reminds us that the universe is far richer and more complex than we dare imagine. We are not merely observers of this vast expanse. We are participants in a dialogue between the known and the unknown, forever seeking answers to questions whose full scope we have yet to grasp. As we stand at the threshold of this cosmic mystery, the question arises: what does it mean to know something we cannot see? The pursuit of dark matter embodies the essence of scientific inquiry, a relentless drive to illuminate the shadows of ignorance. Yet in doing so, we confront the limits of human perception. Our senses, evolved to navigate the tangible world of light and sound, are ill-equipped to grasp the subtleties of the dark sector. We must rely instead on abstract mathematics and indirect measurements, translating the silent language of the universe into symbols and equations. This endeavor echoes ancient philosophical inquiries into the nature of reality, from Plato's allegory of the cave to Kant's critique of pure reason. Thinkers have grappled with the tension between appearances, underlying truths. In the case of dark matter, the cave metaphor takes on new resonance. We peer at the flickering shadows of galaxies on the walls of our observable universe, striving to reconstruct the unseen forms that cast them. The quest to unravel the dark sector is thus not merely a scientific endeavor, but a philosophical pilgrimage, a testament to humanity's capacity to transcend sensory limitations through reason and imagination. Yet, for all our progress, the dark sector remains a reminder of the vastness of the unknown. It challenges us to embrace humility, to recognize that our knowledge is but a fragment of a vaster whole. And in this recognition, we find not despair, but wonder, a sense of connection to a universe that continues to inspire awe and curiosity. With this contemplative spirit, we turn to the next chapter of our journey, where the interplay between science and philosophy will guide us deeper into the heart of existence. In the vast expanse of the cosmos, where stars blaze like distant beacons and galaxies spiral in silent dance, lies a profound enigma, the unseen majority, dark matter, that elusive substance, which constitutes approximately 85% of the universe's mass, defies direct observation, yet shapes the very fabric of existence. Its presence is inferred through the gravitational tides it stirs in the cosmos, the way galaxies cling together in clusters, the subtle warping of light as it journeys across space. Yet despite its dominance, dark matter remains invisible to our telescopes, intangible to our instruments, and inscrutable to our minds. This paradox forces humanity to confront a fundamental question: what is the nature of reality when the bulk of it lies beyond our sensory reach? The challenge posed by dark matter is not merely scientific. It is philosophical. From the earliest civilizations gazing at the night sky to modern astrophysicists probing the depths of space-time, humans have sought to define the boundaries of the known and the unknown. But dark matter blurs those lines, revealing a universe far stranger and more complex than once imagined. It whispers of hidden dimensions, unseen particles, and laws of physics yet to be discovered. In its shadow, we find ourselves adrift in a sea of uncertainty, questioning whether the universe is a tapestry woven from both the visible and the invisible, or if our perception is but a narrow slice of a vaster truth. This tension between what we can observe and what we must infer has shaped the trajectory of scientific inquiry. The ancient Greeks pondered the nature of atoms, unseen yet foundational to all matter. Newton's gravity explained planetary motion without revealing the mechanism behind it, and Einstein's relativity redefined space and time as dynamic entities rather than static stages. Each breakthrough emerged from a willingness to embrace the unseen, to trust in patterns and equations as guides to reality. Now dark matter stands as the latest frontier, a cosmic riddle that demands we refine our tools, broaden our theories, and perhaps redefine what it means to know. Yet the struggle to comprehend dark matter is not solely a matter of intellectual pursuit. It is an existential reckoning. When we realize that the stars, planets, and life itself are mere flecks of ordinary matter in a sea of the unknown, we are humbled by the scale of the universe. We are reminded that our senses, evolved for survival in a terrestrial world, may be ill-equipped to grasp the full breadth of cosmic reality. And yet this limitation is also a catalyst, a spark that propels us to innovate, to explore, and to seek answers in the shadows. As we stand at the threshold of this mystery, we must ask, is dark matter a mere placeholder in our incomplete understanding? Or does it point to a deeper, more intricate design of the cosmos? The answer may lie not only in the data we collect, but in the way we choose to interpret it. To grapple with dark matter is to confront the limits of human knowledge, to acknowledge that the universe is not only larger than we imagine, but stranger, and to embrace the wonder of a reality that refuses to be fully revealed. The search for dark matter is a continuation of humanity's age-old quest to peer beyond the veil of appearances, like the prisoners in Plato's allegory of the cave, who mistake shadows on a wall for reality. We too may be constrained by the limitations of our perception. In the dialogue, Plato imagines individuals bound within a cavern, seeing only flickering images cast by unseen objects. Only when one prisoner breaks free, turns to face the fire, and eventually steps into the sunlight does the true nature of reality become apparent. This metaphor resonates deeply with modern physics, where the interplay between observable phenomena and hidden causes mirrors the journey from shadow to enlightenment. Dark matter exemplifies this duality. While we cannot see it directly, we detect its influence through the gravitational forces it exerts on visible matter. The first hints of its existence emerged in the 1930s, when Swiss astronomer Fritz Zwicky observed discrepancies in the velocities of galaxies within clusters. He noticed that the galaxies were moving faster than expected based on the visible mass alone, suggesting the presence of unseen mass, what he termed dark matter, to provide the necessary gravitational glue. Decades later, Vera Rubin's studies of galaxy rotation curves reinforced this conclusion. She found that stars in spiral galaxies orbit their centers at speeds inconsistent with the distribution of visible matter, implying an invisible halo of mass surrounding each galaxy. The evidence for dark matter has since grown through multiple independent lines of inquiry: gravitational lensing, the bending of light by massive objects, provides another window into its existence. When light from distant galaxies passes through a foreground cluster, it is distorted into arcs and smeared patterns, a phenomenon predicted by Einstein's general theory of relativity. By mapping these distortions, astronomers can reconstruct the distribution of mass in the cluster, revealing that most of it is invisible. Similarly, observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, indicate that dark matter played a crucial role in the formation of large-scale structures. Without its gravitational pull, the primordial density fluctuations would not have coalesced into galaxies and galaxy clusters. Yet despite these compelling clues, dark matter remains as elusive as ever. Unlike ordinary matter, which interacts with light and electromagnetic forces, dark matter appears to interact only through gravity and possibly the weak nuclear force. This makes it nearly impossible to detect directly, as it neither emits nor absorbs photons. Scientists have constructed underground detectors, such as the Large Underground Xenon MAPS experiment and the Xenon collaboration, in hopes of capturing rare collisions between dark matter particles and atomic nuclei. So far, these efforts have yielded no definitive signals, though they have placed stringent constraints on the properties of dark matter candidates. Theoretical physicists have proposed various models to explain dark matter's nature, from weakly interacting massive particles, WIMPs, to Axions, hypothetical particles that arise from certain extensions of the standard model of particle physics. Some theories suggest that dark matter might consist of primordial black holes formed in the early universe, while others propose modifications to gravity itself, such as modified Newtonian dynamics, MOND. These hypotheses reflect the creative tension between empirical evidence and theoretical speculation, a tension that has defined the scientific method for centuries. The parallels between dark matter and earlier scientific revolutions are striking. Consider the Higgs boson, a particle postulated in 1964 to explain how elementary particles acquire mass. For nearly 5 decades, the Higgs remained a theoretical construct, its existence confirmed only in 2012 at the Large Hadron Collider. Similarly, dark matter represents a leap of faith, a belief that the universe is governed by principles beyond our immediate experience. Just as the discovery of the Higgs validated the predictive power of quantum field theory, the eventual detection of dark matter could revolutionize our understanding of cosmology and particle physics. But the journey from hypothesis to verification is fraught with uncertainty. As physicist Richard Feynman once remarked, science is the belief in the ignorance of experts. In the case of dark matter, this sentiment rings particularly true. Every generation of scientists inherits a body of knowledge that is both robust and incomplete, and the challenge lies in distinguishing between settled truths and provisional explanations. The history of science is replete with examples of once accepted paradigms being overturned by new evidence. Ptolemaic geocentrism, Newtonian determinism, and even Einstein's own reluctance to accept quantum mechanics. Dark matter may well be another such turning point, a puzzle whose resolution will reshape our cosmic worldview. To navigate this uncertainty, scientists rely on a combination of experimental ingenuity and theoretical rigor. Instruments like the James Webb Space Telescope, designed to probe the faint glow of the early universe, and the upcoming Euclid mission, aimed at mapping the distribution of dark matter through weak gravitational lensing, represent cutting-edge efforts to bridge the gap between observation and theory. Meanwhile, particle accelerators and underground detectors continue the search for direct interactions, pushing the boundaries of what is technologically feasible. The pursuit of dark matter is thus a testament to human perseverance and imagination. It is a reminder that the universe does not yield its secrets easily, and that progress often requires patience, creativity, and a willingness to revise our assumptions. In this endeavor, we follow in the footsteps of those who came before us, philosophers who contemplated the void, mathematicians who dreamed of unseen symmetries, and explorers who ventured into the unknown. Their legacy is a shared conviction that the universe, for all its mysteries, is not beyond comprehension, but rather a vast and intricate puzzle waiting to be solved. The implications of dark matter extend far beyond the realm of astrophysics. challenging not only our scientific frameworks, but also our philosophical conceptions of reality. At its core, dark matter forces us to grapple with the unsettling possibility that much of the universe exists in forms and dimensions that lie entirely beyond our sensory capabilities. If 85% of the mass in the cosmos is invisible, then our understanding of the physical world is, by necessity, incomplete. This realization invites a profound reflection. Are the laws of physics we've meticulously constructed over centuries truly universal, or are they merely approximations that apply to a fraction of the cosmic tapestry? Such questions ripple outward, touching on the nature of consciousness, the limits of human cognition, and the very definition of existence. One of the most striking philosophical implications of dark matter is its challenge to the notion of materialism, the idea that all phenomena can be reduced to physical processes. If the majority of the universe is composed of an entity that does not interact with light or ordinary matter, except through gravity, then our traditional categories of matter and energy may be insufficient to describe the full spectrum of reality. This opens the door to speculative theories, such as the possibility that dark matter is a manifestation of higher dimensional physics, or that it interacts with other universes in a multiverse framework. These ideas, while currently lacking empirical support, are not dismissed outright by scientists because they emerge from the same mathematical rigor that has historically led to groundbreaking discoveries. Moreover, dark matter's invisibility compels us to reconsider the relationship between perception and truth. Throughout history, humans have assumed that what we can see, touch, or measure defines the boundaries of reality. Yet, the discovery of dark matter underscores the fallacy of equating perception with existence. Consider the invisible forces that shape our daily lives: magnetic fields, radio waves, and the subatomic particles that constitute the building blocks of matter. These entities are not only undetectable by unaided senses, but are also essential to the functioning of the universe. In this light, dark matter is less an anomaly and more a natural extension of the pattern that has always been present in science, that the most fundamental aspects of reality often remain hidden until our tools and theories evolve enough to reveal them. This line of thought intersects with the philosophy of science, particularly the debate over realism versus instrumentalism. Realists argue that scientific theories aim to describe an objective reality, while instrumentalists view theories as useful fictions that predict phenomena without necessarily corresponding to undeniable truths. Dark matter sits at the crossroads of these perspectives. On one hand, its gravitational effects are undeniably real, shaping the orbits of galaxies and the structure of the cosmos. On the other hand, its composition remains a mystery, and its existence is inferred rather than observed directly. This duality raises questions about the criteria we use to define knowledge. If a theory successfully predicts observable outcomes, does it matter whether the entities it posits are directly detectable? Or is the absence of direct evidence sufficient reason to doubt their ontological status? The implications of dark matter also extend to the nature of human curiosity and the drive to explore the unknown. The fact that we have devoted immense resources and intellectual energy to understanding an entity we cannot see speaks volumes about the human condition. It reflects a deep-seated need to make sense of the world, to impose order on chaos, and to transcend the limitations of our biological senses. This pursuit is not unique to science. It is mirrored in art, religion, and philosophy, where the unseen is often imbued with meaning. In this sense, dark matter serves as a metaphor for the broader human quest for understanding, a reminder that the act of seeking answers is as vital as the answers themselves. Furthermore, dark matter challenges our anthropocentric worldview, the tendency to assume that the universe is structured in ways that align with human intuition. The idea that the cosmos is predominantly composed of an invisible substance defies the logic of our everyday experiences, where visibility and tangibility are synonymous with existence. This dissonance forces us to confront the possibility that the universe operates according to principles that are fundamentally alien to our cognitive frameworks. In doing so, dark matter becomes a humbling reminder of the vastness of the unknown and the limitations of our ability to conceptualize it. The philosophical implications of dark matter are further amplified by its potential role in the ultimate fate of the universe. If dark matter is indeed a form of cold, non-interacting mass, its gravitational influence will continue to shape the expansion of the cosmos for billions of years to come. This raises profound questions about the long-term destiny of existence. Will the universe collapse under its own weight, expand into an eternal void, or undergo some other transformation yet unimaginable? The answers to these questions may lie not only in the properties of dark matter, but in the broader context of dark energy, the mysterious force driving the accelerated expansion of the universe. Together, these enigmatic components form a cosmic equation whose solution may determine the fate of all that is. At the heart of these inquiries is a recurring theme: the interplay between knowledge and humility. The more we learn about the universe, the more we recognize how little we truly understand. This paradox is both a source of frustration and a wellspring of inspiration. It reminds us that the pursuit of knowledge is not a linear march toward absolute truth, but a continuous process of refinement and revision. In the face of dark matter, we are confronted with the humility of our position as temporary observers of an infinite and largely hidden cosmos. Yet, this humility is not a weakness. It is a strength that fuels the relentless curiosity that has driven human progress for millennia. Ultimately, dark matter serves as a mirror, reflecting not only the structure of the universe, but the structure of our own minds. It compels us to question the boundaries of science, to embrace the unknown, and to seek meaning in the shadows. In doing so, it reaffirms the enduring truth that the universe is not merely a collection of objects to be catalogued, but a vast enigmatic story in which we are both participants and interpreters. The journey to understand dark matter is, in many ways, a journey to understand ourselves, our place in the cosmos, our capacity for wonder, and our unyielding desire to uncover the truths that lie just beyond our sight. As we stand at the precipice of understanding dark matter, the path forward leads us to the dawn of the universe itself. The echoes of dark matter reverberate through the cosmic timeline, imprinting their presence on the earliest moments of creation. To trace these echoes is to embark on a voyage through time and space, beginning with the cosmic microwave background, a relic of the universe's infancy, imprinted with the gravitational fingerprints of dark matter. This faint glow, a whisper from an era when the universe was a seething plasma, holds within it the seeds of structure, the blueprint of galaxies, and the silent scaffolding upon which the cosmos was built. The interplay between dark matter and the early universe is a tale of symmetry and asymmetry, of forces that shape the heavens in ways we are only beginning to comprehend. In the first fraction of a second after the Big Bang, the universe expanded at an unfathomable rate, stretching quantum fluctuations into the vast web of density variations that would later give rise to stars and galaxies. Dark matter, with its unseen gravitational pull, acted as a cosmic architect, guiding the collapse of ordinary matter into the luminous structures we observe today. Without it, the universe would be a barren expanse, devoid of the celestial bodies that define our cosmic home. Yet, this transition from the invisible to the visible is not merely a story of physical processes. It is a narrative of discovery, of humanity's relentless pursuit to decode the universe's origins. The tools we now employ, telescopes that pierce the veil of time, particle accelerators that recreate the conditions of the early universe, and supercomputers that simulate the dance of dark matter and light, are testaments to our ingenuity and determination. They allow us to glimpse the past, to witness the birth of galaxies, and to unravel the mysteries that dark matter has kept hidden for eons. As we prepare to explore the dawn of time, we carry with us the lessons of our journey thus far. The realization that much of the universe remains unseen is not a barrier, but a catalyst, urging us to refine our methods, to push the boundaries of our knowledge, and to embrace the unknown. The next segment will take us deeper into the cosmic tapestry, tracing the threads of dark matter from the present moment back to the fiery beginnings of existence. Here we will encounter the cosmic microwave background, the first light of the universe, and the intricate interplay of forces that transform the void into the vibrant cosmos we inhabit. In this transition, we are reminded that the study of dark matter is not an isolated pursuit, but a thread woven into the greater narrative of the universe. It connects the present to the past, the visible to the invisible, and the known to the unknown. As we turn our gaze to the dawn of time, we step into a story that is both ancient and unfolding, a story where every answer gives rise to new questions, and every discovery deepens our awe of the cosmos. In the grand tapestry of the universe, dark matter remains one of the most enigmatic threads, an invisible force that shapes the very structure of reality. Though unseen by our eyes, its presence is etched into the fabric of space, binding galaxies together, dictating the motion of celestial bodies, and whispering secrets of the cosmos' earliest moments. It is not merely a puzzle of modern astrophysics. Rather, it is a relic of the universe's birth, a fossilized echo of the primordial explosion that set everything into motion. From the swirling arms of spiral galaxies to the delicate filaments of the cosmic web, dark matter's gravitational influence is the silent architect behind the universe's grand design. This elusive substance has no place in our everyday experience, neither absorbing nor emitting light, making it imperceptible to direct observation. Yet its effects are undeniable. The way galaxies rotate, the way clusters hold together against the pull of expansion, all point to an unseen mass far greater than what we can see. This hidden substance accounts for approximately 85% of the universe's total mass, forming an invisible scaffold upon which visible matter is delicately strung. Without dark matter, the universe would lack the gravitational glue necessary to form the vast structures we observe today. Its presence is inferred not through sight, but through its gravitational pull, a subtle, pervasive force that has shaped the cosmos since the very beginning. But dark matter is more than just an unseen mass. It is a key to unlocking the mysteries of the universe's origin. The distribution of dark matter across the cosmos reflects the conditions of the early universe, preserving the imprints of events that occurred mere fractions of a second after the Big Bang. The subtle ripples in the cosmic microwave background, the faint glow left over from the universe's fiery infancy, align with the patterns of dark matter's distribution. These ancient fluctuations, stretching across the vast expanse of space, reveal the quantum-scale seeds that grew into the galaxies we see today. By studying dark matter, scientists peer into the past, unraveling the story of the universe's birth and the forces that governed its evolution. In this vast cosmic expanse, dark matter stands as both a mystery and a message. It is a testament to the universe's complexity, a reminder that much of reality lies beyond the reach of our senses. As we seek to understand its nature, we are not only probing the depths of the cosmos, but also tracing the path of creation itself. What began as a singularity of infinite density has given rise to the intricate web of galaxies, and dark matter, in its silent vigil, has been the unseen hand guiding this cosmic dance. To understand the role of dark matter in the universe's evolution, one must journey to the earliest moments of existence, when the cosmos was a seething cauldron of energy and space expanded faster than the speed of light. This period of exponential growth, known as cosmic inflation, is believed to have occurred within the first fraction of a second after the Big Bang. During this fleeting instant, the universe underwent an unimaginable transformation, stretching quantum fluctuations, tiny, random variations in energy fields, into vast regions of space. These fluctuations, once microscopic, were imprinted onto the fabric of the cosmos, forming the blueprint for the large-scale structure we observe today. These primordial ripples, though infinitesimal at the time of inflation, would eventually become the seeds of cosmic structure. As the universe expanded and cooled, regions of slightly higher energy density became the sites where matter would later accumulate. However, ordinary matter alone could not account for the gravitational forces needed to bring these regions together into the vast web of galaxies, clusters, and superclusters that now span the cosmos. This is where dark matter plays a crucial role. Unlike ordinary matter, which interacts with light and experiences electromagnetic forces, dark matter is primarily influenced by gravity. As such, it was able to begin clumping together immediately after the Big Bang, forming vast invisible halos that acted as gravitational scaffolds for the formation of visible structures. The cosmic microwave background, CMB, a relic radiation from the universe's infancy, provides compelling evidence of this process, observed as a nearly uniform glow filling the entire sky. The CMB contains tiny temperature fluctuations, differences of just a few thousandths of a degree, that correspond to the density variations imprinted during inflation. These fluctuations, detected by satellites such as the Planck Observatory, match the predicted distribution of dark matter with remarkable precision. They reveal the imprint of quantum fluctuations that were stretched across the cosmos during inflation, forming the initial conditions for the development of structure. Through these temperature variations, scientists can reconstruct the distribution of dark matter in the early universe, tracing the evolution of the cosmic web from its first flickers of existence. As the universe continued to expand, these density variations in dark matter guided the motion of ordinary matter. Baryonic matter, comprising protons, neutrons and electrons, was initially too hot and diffused to collapse under gravity on its own. However, the gravitational pull of dark matter provided the necessary framework for gas clouds to coalesce, forming the first stars and galaxies. Over billions of years, the interplay between dark matter and ordinary matter sculpted the universe into the intricate architecture we see today. The gravitational influence of dark matter continues to shape the cosmos, ensuring that galaxies remain bound together and that the great cosmic structures maintain their coherence despite the relentless expansion of space. Moreover, the study of the CMB allows astronomers to probe the properties of dark matter in ways that go beyond mere observation. By analyzing the subtle distortions in the CMB caused by gravitational lensing, where the mass of intervening objects bends the path of light, scientists can map the distribution of dark matter with increasing precision. These maps reveal a vast network of filamentary structures, with dense knots where galaxies have formed and vast voids where they have not. These observations confirm that dark matter is not uniformly distributed, but instead forms a complex web of density peaks and troughs, mirroring the patterns seen in the CMB. Through these cosmic imprints, dark matter emerges not as an abstract concept, but as a tangible force that has shaped the universe's destiny. Its gravitational influence has dictated the formation of galaxies, guided the movement of stars, and preserved the echoes of the universe's earliest moments. As we continue to refine our understanding of dark matter, we are not only unraveling the mysteries of the cosmos, but also deciphering the fundamental forces that govern existence itself. The universe, in all its vastness, is a testament to the unseen hand of dark matter, a silent architect whose influence has endured from the first instant of creation to the present day. Dark matter does more than shape the universe's structure. It carries within it the memory of the first instant, a record of the conditions that gave rise to everything we know. In its silent, invisible embrace, it preserves the echoes of an event so profound and so distant that it defies comprehension. To study dark matter is to peer into the very heart of the universe's birth, to trace the faintest ripples in the cosmic fabric that mark the transition from nothingness to everything. These ripples, born in the quantum chaos of the primordial moment, are not merely relics. They are the language of creation, encoded in the gravitational scaffolding that binds the cosmos together. The universe's earliest moments are shrouded in mystery, a time when the laws of physics as we know them may not have existed in their current form. The extreme energies and densities of the Big Bang likely gave rise to phenomena that lie beyond the scope of contemporary science. Yet, within the intricate patterns of dark matter's distribution, we find tantalizing clues about these enigmatic conditions. The density variations in dark matter, preserved over billions of years, may reflect the quantum fluctuations that emerged in the first split second of the universe's existence. These fluctuations, stretched across the cosmos during inflation, are not random, but are imprinted with the characteristics of the physical processes that governed the universe at its inception. By studying dark matter, scientists hope to decode these quantum imprints and uncover the mechanisms that triggered the universe's explosive birth. One of the most profound implications of dark matter lies in its potential to shed light on the nature of the Big Bang itself. Was the universe born from a singularity, as the classical model suggests, or did it emerge from a different kind of quantum state? The distribution of dark matter offers hints that the universe's origin may not be as simple as previously thought. For instance, Certain anomalies in the cosmic microwave background suggest that the universe may have undergone a phase before the Big Bang, a concept explored in theories such as the ekpyrotic model or the cyclic universe. In these scenarios, the universe is not a one-time event, but part of an eternal cycle of expansion and contraction. If true, dark matter could serve as a bridge between these cycles, carrying the imprints of previous universes into the next. Such a notion challenges the traditional view of the Big Bang as a singular beginning and opens the door to the possibility that the universe is far older and far stranger than we imagine. Beyond the question of the universe's origin, dark matter may also provide insights into the fundamental forces that govern reality. One of the most pressing questions in modern physics is the unification of general relativity, which describes the behavior of gravity on cosmic scales, with quantum mechanics, which governs the subatomic realm. The two theories are fundamentally incompatible, yet both are essential to our understanding of the universe. Dark matter, with its mysterious properties and gravitational dominance, may offer a pathway toward reconciling these disparate frameworks. Some physicists propose that dark matter could be composed of particles that interact via forces beyond the standard model of particle physics, such as supersymmetry or extra dimensions. These hypothetical particles, if discovered, could provide a missing link between the macroscopic and microscopic worlds, revealing the underlying unity of the universe's forces. Furthermore, the study of dark matter may help resolve one of the most perplexing problems in cosmology, the nature of dark energy. While dark matter accounts for the majority of the universe's mass, dark energy is responsible for its accelerating expansion. Together, these two entities make up over 95% of the universe's total energy content, yet their relationship remains poorly understood. Some theories suggest that dark matter and dark energy are connected, perhaps through a shared mechanism that governs the universe's evolution. Others propose that dark matter could play a role in modifying the laws of gravity on cosmic scales, offering an alternative explanation for the observed acceleration. By probing the properties of dark matter in greater detail, scientists may uncover the hidden dynamics that drive the universe's expansion, potentially rewriting our understanding of gravity itself. The search for dark matter is not confined to the realm of theoretical speculation. It is an active pursuit that spans multiple disciplines, from particle physics to observational astronomy. Experiments such as the Large Underground Xenon LUX and the Xenon collaborations aim to detect dark matter particles directly by observing their interactions with ordinary matter. These experiments rely on highly sensitive detectors buried deep underground to shield them from cosmic rays and other sources of interference. So far, no conclusive evidence has been found, but the absence of results is itself informative, helping to constrain the possible properties of dark matter. Meanwhile, indirect methods, such as observing the effects of dark matter on the motion of galaxies or detecting gamma rays produced by dark matter annihilations, offer complementary approaches to the problem. In addition to laboratory-based searches, astronomers are turning to the cosmos itself for answers. The James Webb Space Telescope, with its unprecedented ability to peer into the early universe, is providing new insights into the formation of the first galaxies and the role dark matter played in shaping them. By studying the distribution of dark matter in these nascent structures, scientists hope to test the predictions of inflationary theory and refine our understanding of the universe's evolution. Similarly, upcoming surveys such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time will map the distribution of dark matter across the cosmos with unparalleled precision, enabling researchers to trace its influence on the large-scale structure of the universe. As these efforts continue, the implications of dark matter extend beyond the boundaries of science into the realm of philosophy and existential inquiry. What does it mean that the majority of the universe is made up of something we cannot see or touch? How does the existence of dark matter challenge our perception of reality and our place within it? These questions, while deeply rooted in science, resonate on a human level, reminding us of the vastness of the unknown and the limits of our knowledge. Dark matter is not just a scientific puzzle. It is a mirror reflecting the humility of our understanding and the boundless potential of discovery. Ultimately, dark matter represents the frontier of our cosmic exploration, a reminder that the universe is far more complex than we can currently comprehend. Its study is a journey into the unknown, a quest to unravel the mysteries of existence and to glimpse the forces that have shaped the cosmos since its inception. In its silent, invisible presence, dark matter whispers the story of creation, inviting us to listen with wonder and curiosity. As we strive to understand its nature, we are not only deciphering the laws of the universe, but also confronting the fundamental question of what it means to exist in a cosmos that is as vast, as strange, and as beautiful as the one we inhabit. As we stand at the threshold of the unknown, gazing into the vast expanse of the cosmos, we are reminded that the universe is not merely what we can see. It is a realm of hidden forces and unseen structures, a symphony of matter and energy playing out in the silent dark. Dark matter, in its enigmatic stillness, has revealed to us the unseen scaffolding upon which the cosmos is built, a vast invisible framework that binds galaxies together and guides the unfolding of cosmic history. It has shown us that the universe is far richer than our senses can perceive, that the greatest truths lie beyond the reach of light, waiting to be uncovered by the tools of reason and imagination. Yet, even as we have begun to glimpse the nature of dark matter, we are but at the edge of understanding. The universe, in all its grandeur, remains a tapestry of mystery, woven from threads we have yet to fully grasp. The same forces that gave rise to dark matter may also shape the very fabric of reality in ways we have not yet imagined. Perhaps dark matter is not the end of our cosmic journey, but rather a doorway to even deeper questions about the nature of time, the origin of the universe, and the fundamental laws that govern existence. Each answer we uncover leads to new questions, each discovery a step further along the path of exploration, a step closer to comprehending the vast and intricate design of the cosmos. In this ever-expanding pursuit of knowledge, we are not merely observers, we are participants in the unfolding story of the universe. Every telescope that peers into the distant past, every experiment that seeks to detect the faintest traces of the unseen, every calculation that models the evolution of the cosmos, is a testament to our enduring curiosity. We are drawn to the stars not only because they shine in the night sky, but because they remind us that there is always more to discover, that the universe is a boundless expanse of wonder, and that our journey of understanding is far from complete. And so, as we turn our attention to the next chapter of this cosmic odyssey, let us carry forward the spirit of inquiry that has brought us to this moment. The universe is vast, its secrets many, but it is in our nature to seek them out, to reach beyond the visible, to explore the unknown. The story of the cosmos is not one of finality, but of endless possibility, and in the silent echoes of dark matter, we hear the call to continue, to look deeper, to dream further. For in the act of discovery, we do not merely learn about the universe, we come to understand ourselves, our place within it, and the infinite potential that lies ahead.